Very good morning to all of you. On behalf of Rayagada Autonomous College, I welcome all of you to the international webinar on nuclear energy, prospects and challenges. Respected Principal Madam of Rayagada Autonomous College, respected conveners of the webinar, Dr. Arun Kumar Misra sir, Professor Arun Kumar Khadanga sir, Organizing Secretary, and all other supporting members of the webinar. We are going to start the program, and I request our Honorable Principal, Professor V.R. Ratnasri Madam, to give the inaugural address.
Thank you, Pradeep sir. A very good morning to one and all. It gives me immense pleasure to be a part of this webinar. So let me begin with the introduction of our college, which was established way back 1966 in a remote corner, the southern part of Odisha, that is Rayagada. It has around 57 teaching staff and 50 non-teaching staff. Around 5,000 students are on rolls with 19 departments starting from +2 degree undergraduation and post-graduation, and it is preparing for its third cycle of NAC. In the last second NAC visit, it could secure the B grade, and we are trying our level best to upgrade it further. And before I start, I would like to welcome one and all to this international webinar. I would like to express my highest appreciation to the departments of chemistry and physics of our college for venturing such an international webinar during this world pandemic, where we are not having physically or literally normal classes, and we are having a lot of health hazards throughout the world, but still hats off to our two departments for organizing this. And coming to, in a brief, I would like to speak few words so far as this topic is concerned, because I don't have expertise in this topic, but still I'd like to express few of my points. So coming to the global economy, it was earlier the economic growth was around 8% to 9%, but now it has reduced to a lot. And generally, it is believed that the economic growth is based on the consumption of electricity. And where from this electricity is generated is believed to be the fossil fuels. And in the present day context, it's becoming difficult day by day to have this in sufficiency, but still we have to promote, we have to bolster and see that the development is not hampered, the growth is not affected, and the developmental activities will continue. It is said about 80% of the electricity is produced or is producing electricity or generated by the fossil fuels, 18% by the renewable sources like solar power, hydroelectric power, wind energy, and biomass power. Whereas the nuclear energy is said to be nearly 2%, or 2.3%. And for decades from now, I'm sure by now already it is dwindled, the fossil fuels and others. And in decades from now, it is definite that we may not be in a position to get electricity generation sufficiently. So the only alternative is nothing else but the nuclear energy. And in order to exploit the available nuclear fuel resources for energy production, a three-stage nuclear program has been envisaged in India. It is the brainchild of Dr. Homi J. Bhabha in around 1950s. Now about 13.5 of the total electricity is generated worldwide is from nuclear reactors. And there are around 430 commercial nuclear reactors operating in 31 countries. In India, around 20 reactors are under activity or operation, and 7 reactors are under construction. In the long run, as such, it's nuclear energy, which is the only sustainable energy. Once again, I am saying, available to meet India's growing energy demands. An article titled "The Future of Nuclear Energy in India" by Anirudh Mohan for Observer Research Foundation, which reads, I quote, "Perhaps the most important source of energy for India in the coming decades is nuclear power, given its huge potential for growth, emission, free nature, and consistent nature of production. A significant separation of nuclear power can both enable the connectivity of millions of Indians who currently lack access to the power grid and help it contribute to global efforts to tackle, eliminate change by curbing its total carbon emissions." This webinar will be focusing on the prospects and challenges associated with nuclear energy. Today, around 6 countries in the world and from within the state, 16 states are joining or otherwise have joined this webinar. Apart from that, a huge number of professors, scholars, specialists, PG and UG students, and many more from various disciplines are participating in this webinar. I wish that almost everyone who are participating or who is participating in this webinar will be enriched to the extent possible. I once again thank our physics and history departments for giving me a chance. Though I don't belong to this departments. I am totally from a different stream, that is arts. They have encouraged me to participate. I am very much thankful to one and all. And I welcome you all again. Thank you very much for the patient hearing. Thank you. I wish a grand success for the webinar. And one more point, I would like to invite other departments to follow this and let this be the precedence in this pandemic. Thank you.
Thank you, madam, for your nice inaugural address. You have been the source of inspiration for us. Without your support, probably we could not have thought of starting this webinar. Thank you, madam. Now I request Dr. Arun Kumar Misra, sir, head of the Department of Chemistry, to give the welcome address.
Good morning to all the participants of the webinar from India and abroad. Esteemed Principal, Madam B. Ratnasri of Rayagada Autonomous College, Rayagada, Odisha. Eminent speakers from India, Dr. C.H. Jagadeshwar Rao, Scientific Officer, E. Indira Gandhi Center for Atomic Research, Kalpakkam, Tamil Nadu. And from overseas, Professor Dr. M.B. Ramana from University of British Columbia, Canada, which is among 20 top universities in the world. Respected professors, readers, lecturers, scientists, scholars, and my dear students, on behalf of Department of Physics and Chemistry, I welcome you all to this international webinar on nuclear energy, prospects and challenges. The main purpose of convening this webinar is to acquaint the young scientists, scholars, and students about the recent development and research in the field of nuclear energy. At the same time, to remind the devastating effect of nuclear warfare, which can be learned from Hiroshima and Nagasaki incidents during World War II on the date 6th and 9th August 1945. In my opinion, at this crucial juncture, where the coronavirus pandemic has engulfed the whole world and the casualty has risen to more than 11 lakhs in the world and 1,18,000 in India. In this situation, countries like America, China, India, Pakistan, France, Russia, UK, and Israel possessing nuclear weapons and performing their nuclear tests from time to time to show their power and position. These countries may use anytime the nuclear weapons and will bring mass destruction. They should not forget the NPT treaty, non-proliferation of nuclear weapons, and they should refrain from the nuclear warfare. My second point, nuclear or atomic energy produced by the phenomena of nuclear fission and fusion should be used in the constructive way for the production of atomic power. It meets 13.5% of clean electricity in the world and 3.22% in India. It should find use in the field of medicine for the treatment of diseases like cancer, thyroid, and many more. Also find use in space exploration and desalination of water. Today is on this day, 24th October 1945, it was formed for the progress and peaceful purpose of the world. So now we must take an oath to harness the nuclear energy for the progress and peaceful purpose of the human being. Thanking you, sirs.
Thank you very much, sir. Now I request Professor Arun Kumar Khadanga, sir, head of the Department of Physics, to give a brief overview of the seminar topic. Sir, please.
Good morning to all. Esteemed Madam Srimati B.R. Ratnasri, Principal of Rayagada Autonomous College, Rayagada, and Chief Patron of this international webinar. Respected Honorable Speaker, Professor M.B. Ramana, Professor and Senior Chairperson, SPPGA Director, Leo Institute for Global Issues, University of British Columbia, Dr. C.S. Jagadishwar Rao, Scientific Officer, MMG, Indira Gandhi Center for Atomic Research, Kalpakkam, Tamil Nadu, Co-Convener, Dr. A.K. Mishra, Coordinators and Organizing Secretaries, Dr. P.K. Samantra, Department of Chemistry, and Sumant Kumar Sahu, Department of Physics, my beloved colleagues, friends, students, participants from all places of India as well as abroad. I heartily welcome all participants to this international webinar. Really, I am very much thankful to Professor M.B. Ramana sir and Jagadishwar Rao sir for their support in holding such type of human beneficial international webinar. Further, I extend my gratitude to Dr. Manasi Mahanti, lecturer in political science, and my younger brothers, Dr. P.K. Samantra and Sumant Kumar Sahu, who has taken a lot of pain and made this event success. Nuclear energy is the atomic energy released in a huge amount, which comes from nuclear fission and nuclear fusion. The amount of energy released due to fission of one uranium atom is about 200 million electron volt, while energy released due to fusion of 4 hydrogen nuclei is about 26.7 MeV. Energy released in fusion is more tremendous. In fission reaction, a heavier nuclei splits into lighter nuclei, and in fusion reaction, lighter nuclei combine to form a heavier nuclei, releasing huge a tremendous amount of energy. Nuclear energy is very dangerous and harmful to mankind. Nuclear energy is used as electrical energy in different places throughout the world. The advantages of nuclear energy, it is low cost, reliable, zero carbon emission. You know, carbon emission destroys the air pollution, creates the air pollution. So being it is a zero carbon emission, so nuclear energy is a benefit to mankind, high energy density, environment impact, and the risk of nuclear accidents. The energy released in a nuclear reaction, basing upon the most important formula mathematically written by Einstein, E equal to mc square, where E is energy released, m is the mass, and c is the speed of light. That is, the mass is converted into energy, or vice versa. Being carbon-free electric source that can widely expand to provide large amount of electricity. The disadvantages are the harmful to human body in both pathological and genetic effect, expensive to build, accidents, produces radioactive waste, impact on environment, security threat, and limited fuel supply. Around world, 17 countries like United States, France, Russia, South Korea, Germany, China, Canada, etc. are using nuclear energy in the form of electrical energy. In India, 22 nuclear reactors in 7 nuclear power plants with a total capacity of 6,780 megawatt. Tamil Nadu produces largest nuclear energy, that is 2,000 megawatt for power generation. Largest thermal power station is at Vindhyachal at Madhya Pradesh. Calcutta is the first city in India to get electricity from nuclear energy. I will not take much more time, and we are eagerly waiting to listen from our guests about their topic, nuclear energy, prospects and challenges. Once again, I thank all my lovely participants. Please enjoy this session and learn more and more. I welcome all of you to this event. Thank you all.
Thank you very much, sir, for your overview on the nuclear energy. Now we will move to the technical sessions, and I request the first speaker of the session, Dr. C.H. Jagdishwar Rao sir, to take over. But before that, it is my pleasure to give a brief biodata about Dr. Jagdishwar Rao. He has obtained his master's degree in organic chemistry in 2001 from Andhra University, Visakhapatnam. Then completed his B.Ed in physical sciences in 2003, and he has obtained his PhD in chemical sciences from University of Madras in 2011. He has pursued his PhD on the application of room temperature ionic liquids for nuclear fuel reprocessing and waste management at Indira Gandhi Center for Atomic Research, Kalpakkam, Tamil Nadu. He joined the Corrosion Science and Technology Division as a scientific officer in 2012, and currently he is working as scientific officer E at IGCAR Kalpakkam. He is also the assistant professor at Homi Bhabha National Institute, University, Mumbai. He is actively working in the area of development of corrosion protection coatings and air and stream oxidation studies of structural materials for nuclear reactor and reprocessing applications. He has 32 peer-reviewed journal publications and 1 Indian patent to his credit. But more than that, knowing Dr. Jagdishwar Rao personally, I would say, sir, you ask any research scholar from the research scholars enclave from Kalpakkam, the first thing they will say is Dr. Jagdishwar Rao is a wonderful human being. So it's a pleasure to know you personally, sir, and I request you to deliver your talk on the topic nuclear energy, a clean and sustainable energy. Sir, please.
Thank you, Dr. Pradeep. And I thank all the organizing members of Rayagada College, Autonomous College, for inviting me for delivering a talk related to nuclear energy. But my job was made very simple by the principal madam and HODs who spoke about nuclear energy a lot. And I really appreciate the knowledge they have, the awareness they have about the nuclear energy. So I thank once again Dr. Pradeep. He is my colleague and friend, where we did together PhD, and I joined later in IGCR for his invitation. So we will start the presentation. So good morning once again, all of you. Am I audible?
Yes, sir, it is audible.
Okay, okay. Thank you, thank you. So today I am going to speak about nuclear energy, a clean and sustainable energy. As you understood from the organizing committee, they already spoke about it. We will go through some more details. So the doc may cover the following points like nuclear energy and overview, and some of the facts and myths about the nuclear energy and radiation in the society, which we will try to give some input about that, and then what type of nuclear fuels and will be used for generating nuclear energy in a type reactors. We have several types of reactors, and about Indian nuclear power program. Then we will go for the conclusive remarks at the end. To start with, the energy released during nuclear reactions. You see, generally when we studied chemistry from a school level, we know that most of the time, all the chemical reactions involve the electrons, which rotates around the nucleus. but we never heard about much about the nucleus reactions. So in the nucleus, as you know, that there are nucleons, there are protons and neutrons. So those also can hold a lot of energy. That energy will be harnessed in this nuclear reaction. So the energy comes from a nucleus of atom is the one which will be used for the generation of nuclear power. How it will be seen? There are two ways, as already spoken in the introduction, about nuclear fission and nuclear fusion. We will see once we go through the slides. So the nuclear power plant is nothing but where you have, it is like similar to your conventional coal-based power plants or steam power plants, where you will be generating the heat will be carried to generate steam. The steam will go to rotate the turbines. The turbine will give to the generator. Generator will generate the electric power. Nothing else. So in order to know that for nuclear, the main fuel, most of the worldwide use so far is the uranium. So this is the element which was discovered in 1789 by Klaproth. And then the radiation was, X-rays was discovered by Röntgen in 1895. These are the sequence of things. And later, Henry Becquerel in 1896 found that there is a photographic plate becoming dark because of the material he kept on it is called pitch black. Then later, Pierre and Marie Curie, both wife and husband, they found out that phenomenon, and the name of the phenomenon is called radioactivity. In later, in 1938, these are the three guys, Hahn, Meitner, and Strassman. They became the first to recognize that the uranium atom, when bombarded with neutrons, it actually splits and also releases a lot of energy. The Meitner, the one who lady has calculated the amount of energy it releases. The latter, Hahn received the Nobel Prize in 1944 for this particular reaction called nuclear fission. So if you can see the nuclear fuel, when we compare with other fuels, what we used, we generally use firewood in olden days for our daily cooking process. If you take 1 kilo of firewood, it gives 1 unit of power. That is 1 kilowatt hours. That is 1 unit. What we pay for now electricity bill as a 2 rupees of it. That is 1 unit of power you will get out of 1 kg of firewood. But if you take coal, the same 1 kg of coal gives around 3 units. The oil gives around 4 units. But if you come to the nuclear fuel where you have natural uranium and also plutonium, you see the number. So 50,000 units power one can get from 1 kg of natural uranium. Similarly, from plutonium, the number is still huge. So when we compare these conventional fuels, they will release the energy about 0.01% of the fuel what we actually use. But the nuclear, when you use one fuel, it produces 1,000 times of the fuel what we use. That is the advantage. That is the very high energy density of the nuclear fuels. And if you see this as a pictorial representation, I would like to show this. You see the natural uranium, these are the fuel bundles which will be used in the nuclear reactors. You see these two fuel bundles around, for example, 27 kilos, it contains natural uranium. But if you see the coal, if the same amount of power to produce like 1 million units of electricity, you require a coal of 700 tons. But you require just 27 kgs of fuel for a nuclear reactor. So the operation of a 1,000 megawatt electrical plant require only 1 truckload of enriched uranium, that is around 30 tons. And out of this, you see only 4 to 5% of the fuel will be used. Remaining becomes waste. But as for Indian context, that waste once again we are using for getting the fuel for the next generation of reactors. We will see. Next. If you see the nuclear power, there is no doubt that it is the need of the hour. The world requires it. Presently, we are in the spaces. Every country try to go for the space and explore more and more and more. But still, we are using the fossil fuels which thought to be emerged from the Iron Age. You see that the mankind evolution has started from a caveman to the Stone Age, Bronze Age, Iron Age. Now we are in the age where we depends for each and everything on the fossil fuels. So our future generation may thought that they may say that we lived in an age called fossil fuel age. If you continue similarly, even we can enter into a post-fossil fuel age, but we should not. So we should, instead of enter into a green age by reducing the carbon dioxide emissions, greenhouse gas emissions, that can be done only by nuclear fission or other renewable sources. And you know that because of this global warming, the global average temperature has risen by around 1 degree centigrade from 1880s. And for the last few decades, the per decade rise was even higher when compared to olden days. So we need to control our carbon emissions. So the better option, one of the better options could be the nuclear fission power. If you see here, nuclear power should not be afraid of it. The world required it. It needs it. Why? If you can see this picture, capacity factor by energy sources. So if the capacity factor is 100% means the plant is available 24 hours by 365 days for production of power. You see the nuclear power, the capacity factor is 93.5% when compared to all other. Even natural gas is 56 and solar is 24. So no doubt that nuclear power is a better one. And we should not afraid because we know the science. The science behind the nuclear power is actually very simple and very well understood. So the atoms of the nucleus of the atoms contains enormous amount of energy that need to be harnessed in a proper way. It can be used for peaceful uses like producing electricity and also can be used for destruction like atomic bombs. It is our thing that how we want to use. And remember that no reactor, no power reactor, no nuclear power reactor can become as a bomb. People say that it is a bomb. Never. As per IAEA rules and regulations, all the reactors will be constructed and they will not have the fuel which is high pure and highly enriched, which required for the nuclear bomb. So no reactor in any unforeseen condition can't become as a bomb. So we should not be afraid of it. If you see the nuclear fission in detail, like point of view, you see you have a nucleus like 92U235 atom. It will be bombarded with a small neutron, thermal neutron, the energies are less. If you bombard the uranium-235, it becomes 92U236, then it loses its stability. So now this atom becomes unstable. Once it becomes unstable, it breaks into two nucleus, two different nucleus. One is barium, another is krypton. At the same time, good thing is that it is a exothermic reaction. It releases energy, the energy of the order of 200 million electron volts. At the same time, it gives 3 more neutrons. These are the sources for further nuclear reaction to continue, nuclear fission reaction to continue. You can see here these 3 neutrons can individually bombard or collide with another uranium-235 nucleus with 3 different nucleus, and each one can convert into U-236, then further splits and gets 3 more neutrons and 200 MeV of energy. Now you will get a huge amount of energy. It is like our free radical reactions. You see, in the free radical reaction, we say that chain initiation, chain propagation, and chain termination. Is it not? Similarly, this is the initiation of the fission. One neutron, any neutron source can be used to initiate the fission. Once the fission is initiated, it will be continuous, like chain will be propagating in different directions, until you have the fuel. If you don't have the fuel U-235, it cannot continue the chain reaction. So you can terminate the reaction by eating away these neutrons, absorption of these neutrons. You see that the neutrons are not available for the fission, then you are able to control. So that's why I told the chemistry about nuclear energy production or nuclear fission is very, very simple and well understood. And you can control these fission reaction at any point of time. You can terminate the reaction like our Frederick-Klopp's reaction, how you can terminate for polymerization, all these cases. Similarly, you can able to terminate at any point of time. If you are not terminating, if you are leaving to happen, then everything can happen in a fraction of a second and it releases enormous amount of energy and can become as a bomb. That's what the nuclear bomb. But remember, nuclear fission is very well controlled in the nuclear reactors. Okay, we will see. It is not that all the elements, heavier elements, will undergo nuclear fission. There are two types of elements. One is fissile elements, another is petrol elements. You can see these yellow colored one, like natural uranium, which available from the earth crust in the form of pitch blende U3Y, contains mostly 99.97%, 99.9% is uranium-238. Only the fraction 0.7% is uranium-235. That's what we see in the previous one. This uranium-235 is the undergoes fission. That is only around 0.7%. Then you have uranium-238, a huge amount. But this cannot undergo fission. That's why it is called a fertile nucleus, which cannot undergo spontaneous fission by absorption of a neutron. But it can convert into a fissile element like plutonium-239 by some reactions, where you can capture the neutron and gives a gamma and gets uranium-239, then it emits a beta and comes to the neptunium-239, then emits beta particle and gets 239 plutonium. Now this plutonium-239 is a man-made. It is made in the reactor, where you took the 238 and there is a neutron, hits the 238, you get the plutonium-239. This can be used as a, once again, fissile element. It is a fuel for the next stage of the reactors. Similarly, in Indian context, if you can see, we have huge amount of thorium resources. Thoria, THO2, monazite sand in the form of beach sand, where the thorium is also once again not fissile, unfortunately. But we can make it fissile U-233 by these reactions. Neutron absorption capture, then thorium-233 further goes to the beta emission. You can see the particles and the notations I have given here. And beta particle, then it protoactinium, then later beta particle, it goes to the U-233. Now you see, I told the previous slide, uranium-235 is the fissile element. Now U-239 is another fissile element, and U-233 are another fissile. These are the three fissile elements, you can say nuclear fuels, which can undergo spontaneous fission reaction and produces lot of energy and neutrons. But you remember, each one requires different type of neutrons to start the fission. Some require thermal neutrons, some require fast neutrons. The energy should be higher. If you can see here, nuclear fuels. What is a fuel? As we already seen that materials which undergo spontaneous fission is called a nuclear fuel. Anything which undergoes spontaneous fission can be called a nuclear fuel. The nuclear fuel can be in the form of metal. It can be in the form of alloys, 2-3 metals together. It can be in the form of oxide. Most of our nuclear reactors in India or worldwide uses right now oxide fuels. That is UO2 oxide, uranium oxide or plutonium oxide, mixed oxide. But one reactor in our center, Indira Gandhi Center for Atomic Physics, we have a test reactor, fast breeder, which uses a carbide fuel, UC and PUC. So the fuel can be any form. Only the fissile elements undergo fission, as we see. So we seen all these fissile elements, and you see these are the picture shows nuclear fuel pellets around 8 to 15 mm diameter, and length is around 1 inch or less than 1 inch. And they will be packed all these highly sintered pellets into a tube called fuel rod. This fuel rod will be assembled as a group called fuel assembly. It goes into the reactor. We will go through detail the nuclear fuel cycle for better understanding how it works. Then we can clear all our doubts about nuclear energy. you can see the left downmost where first we go for the mining, all the fuels, uranium, everything available on the earth crust, it is more abundant. And you can get the uranium from the mining, then goes for a milling process. You need to process it. Then there is a conversion. You need to convert into the form, whether it is oxide, whether fluoride, what form you require. The conversion then goes for the enrichment. We will see what is enrichment in the next slides. And once it is done, from enrichment you can go to the fuel fabrication, or directly you can go to the fuel. There are two types of reactors. Some reactors use enriched fuel. Some reactors will use natural uranium fuels. So we have, I think it is better we can take all the questions at the end of the talk. Some people have raised their hand. I think better the organizers can decide.
Yeah, I too agree with you, sir. I request all the participants, please keep your questions ready, and we will have a separate question answer session. And at that time, you can have your questions.
Yeah.
Let us give the authority to continue his speech, and we can have the questions later. Thank you.
Okay, thank you, Pradeep. So then after the fuel fabrication, then the fuel will go to the reactor, power reactor, where you get the power energy. Then the used fuel, called as spent fuel, most of the countries, they will just take it away and go for the disposal because they have more resources. But some countries like India, we go for another route called reprocessing. The used fuel will be once again reprocessed and take the good fuel out of it and goes to the fuel fabrication and to the plant. So this cycle will be continued. So the leftovers, very minor amounts, will go to the RACs. In detail, we will see each and every process. It is, you see, uranium mining. A mining will be done first, U3 white fuel, where the uranium found in the mines, the source is around 0.3% to 20%. But remember, India does not have resources where uranium content is higher. Our uranium content in the available source is very, very, very less. But still, we are going for the mining to get the required uranium. Once the mining is done, it will be processed into yellow cake. This is U3O8 cake. Sometimes it is ammonium diurenate cake. It is in the form of yellow, where the uranium content will be more than 80% in this. When you have less than 20% in the mined one, and now you get to the mostly 80% above. This is uranium milling. These cakes, yellow cake, will be packed and sent to another plant called conversion plant, where it will be converted into uranium hexafluoride. Remember, the U3O8 or U2 will be U3O8 is converted into uranium hexafluoride. Why? See, some pressurized water reactors, they require uranium-235, which should be enriched to 3 to 5%. That means I have a natural uranium where I have U235 isotope is around 0.7%. That is not sufficient to act as a fuel in some type of reactors. So you need to increase the 0.7% to more than 2 to 3% or 3 to 5%. For that, you need to increase the isotope concentration, U235. Can be done by using enrichment. The enrichment is done in the gaseous form, diffusion process, or a centrifugal process. There are two processes, we will see. So first one, you need to convert the fuel, whatever this is okay, into uranium hexafluoride, UF6. That gas will be stored in the cylinders and brought to this particular plant is called enrichment plant. Where you can see these columns, all these are centrifugal columns. The gas will be filled in this and they will be rotated with very high velocity such that all the heavier atoms, that is U238, will go and stick to the walls of these containers. Center will be your U235, that will be separated and you will have more enriched fuel where you can do the enrichment up to 3 to 5%. Once the enrichment is done, or directly conversion not required, enrichment is not required. If you want to directly use UO2, you just convert this U3O8 to UO2 by reduction. Once the UO2 is available, whether it is enriched or natural uranium dioxide, Then we go for the fuel fabrication. You see the fuel will be fabricated like this small cylinders. These are all highly sintered. They will be heated at around 1500 above, and compaction will be done. High dense fuel pins, which is full of UO2. These pins will be arranged in a sequence to get the fuel rods. Then, as I previously told, it will be arranged assembly. Then it goes to the reactor. You see, this is the picture, small picture, where you can see all these are arranged hexagonal shape fuel rods in a reactor. If you see the top view of the reactor, this particular one, this is the reactor. You can see the reactor inside. You have a reactor as containment area where you have a port, where you have all these fuel pins will be kept. So this reactor now produces the energy. Nuclear reaction, fission occurs, and it releases energy. The energy will be, it is simple. I will show some of the pictures of the reactors where we can clearly explain still better way. So then after the reaction is over, after the fission is done, the fuel will be per yearly once or 2-3 years once. Some fuel, it is not the full fuel, some of the fuel will be replaced. They will be taken out, the new fuel will be introduced. Once they take the fuel, it will go for the interior storage. This is a pool type storage at the reactor building itself, because the fuel which undergone fission, which is in very high temperatures, and there are a lot of radioactive elements were produced due to the fission. Those are called fission products. So it has more radiation. At the same time, it has more heat. So in order to cool, we are going for an interior cooling facility. It is just simply immersed in a water. Like you take a water well and put it, just immerse it for sufficient time, such that the heat will be decayed. The radiation will decay, all short-lived particles, they will decay. Once that is done, after 2 to 3 years, it will go for another storage. It is a long time storage. It can be wet storage, or this is wet storage, this is dry storage. There are different types of storages will be done. And some countries where they don't use this spent fuel back into the reactor, so they directly go after its sufficient period of cooling, directly go to the deep geological repositories for storing. This is the one where you see these are the panels type was made inside earth in deep areas where you have a rocky structure, and where that will be packed in a properly, and they will go and keep there for a long time. But like India, we go for a reprocessing. You see, this fuel after the sufficient period of like maximum 5 years, we will take it out and takes to the reprocessing plant where you will be reprocessed. Why we need to reprocess? You see the fuel, what I told, for example, if you take a natural uranium fuel we used in the reactor, it contains 99.9% uranium-238, and the rest is only 0.7% 235. And in the reactor, it used only just 3% or something. Remaining uranium is available. And the U-238, as I already seen, previously I showed you, it will absorb the neutrons. Since it is in the reactor, it absorbs the neutrons and converts into plutonium-238. This plutonium is a fissile element, so it is a fuel for the next generation. So we need to reprocess. So the plutonium is around 1% will be there. That has to be reprocessed back, and remaining uranium has to be reprocessed back. So we go for a reprocessing facility where we will be reprocessing. We will see what are the different process by which we can be able to reprocess this. You can see the types of reactors. We also need to know the evolution of the reactors, how they work. Just so you see, there are broadly we can consider thermal reactors and fast. Remember that thermal reactors where the neutrons energy is less, and fast reactors where the input neutrons energy is higher. So they require different types of fuel based on the type of neutrons. If you can go to the first worldwide, most of the reactors are this one, pressurized water reactors. The neutrons are thermal neutrons, where the fuel requirement you can see here 3 to 5% enriched fuel, where the uranium-235 is 3 to 5%. From the natural uranium of 0.7%, we are going to increase to 3 to 5%. And there is a coolant. Coolant is the one which cools and takes away the heat from the nuclear fission and gives the steam and will be turbine, all these things happen. Moderator is the one which controls our nuclear fission reaction. So the both are here is normal water. And next we have boiling water reactors. India having 2 boiling water reactors, where you have once again enriched fuel required, water and coolant are both are moderator and coolant both are normal water. But we have pressurized heavy water reactors. You see, India is having most of the reactors are PHWRs, pressurized heavy water reactors. We have a heavy water board, heavy water plants at different places of India, produces the heavy water which contain DTO, deuterium oxide, where the hydrogen will be replaced with the isotope D, deuterium, and natural uranium is the one which can use. So we don't need to go for the enrichment. So directly you can use the natural uranium. And coolant is deuterium oxide and moderate is water once again. So similarly, we have light water, graphite reactors, advanced gas cooled reactors. India is also having fast breeder reactors. These are all the common type of reactors. But India is also having a fast breeder reactor where the neutrons are fast. But here you see the enrichment is still higher. This cannot be fissioned in these type of reactors, this type of fuel. So you need to go for a very highly enriched fuel. And here the coolants are different. We are using metallic coolants like liquid sodium or liquid lead. But mostly India is using liquid sodium. And there is no moderator is required. If you can see the reactors, I think this picture gives you a clear understanding how the energy is generated in a nuclear reactor. You can see the pressurized water reactor. You see, this is the main reactor pressure vessel. I hope you are able to see this cursor. So this is the reactor pressure vessel where you have kept the fuel over here, and these are the control rods. These control rods are the one, when you insert more, they will eat more neutrons. Neutrons will be less, then you are controlling the fission. So now this reaction, what is happening here, produces the heat. The heat need to be taken out, correct? That's our aim. So here the heat will be, whatever produced will be taken out by using water. Here. This is full of water. Since once the water heated up, what will happen? It produces steam. So this becomes steam. So in order to avoid the production of steam within the reactor, this type of reactor, you are pressurizing the water. Under pressures, the temperature required to make the water to vapor is little higher. That means the water can take more heat, more heat. It can go beyond 100 degrees centigrade. So it is now highly heated water. This water will be transformed through a coil, and where you have a secondary load, where normal plain water comes here, and this water takes away the heat from this particular water which comes from the reactor. So water heat transfer is happening. Whatever this water comes, this pale blue color water now gets heated up and becomes steam. The steam goes into the steam line and it rotates the blades of the turbine. Turbine connected to the electric generator. Generator generates the power. Power connected to the grid. Grid gives to the power to the industry or whatever it is. So this is the water which you require is cooled water. So you have a cooling tower. You can cool the water, or the steam will be cooled down such that water will be condensed back and used. So this is the simple concept where our nuclear reaction is the heat input. Like a thermal reactors, you have coal. Coal will be heated up. The coal heat will be taken similarly. This particular path is common for all the reactors, whether it is thermal or nuclear reactors. The thing here, the heat production is different. You have a nuclear reactor where nuclear fission is the heat producing source. Clear? So now we will go to the next one. You see, this is boiling water reactors. These are like the water which immerse. This, you see, this pale one is the fuel. Correct? So now the rods are inserted from the down, and this is fully immersed in water. It is like a well type. You have well where down is water. You are immersing your fuel bundles in that. Then the nuclear reaction happens. Then the water will be evaporated within the containment itself. You see, this reactor containment itself, the water is evaporated, and the steam only will be you are taking out. There is no heat transfer between another line of water. Directly the steam is taken out. That's why it is called boiling water. It is boiling simply. So that water will go. Then once again the story is same where you have turbine and the power will be generated. So this is boiling water reactors. We have two in India, boiling water type of reactors. Then you have most of our Indian reactors are pressurized heavy water reactor. Here the fuel itself is in a different form. It is a horizontal form, sleeping form. It's called a calandria. The reactor vessel, this particular one is called calandria. Within that you have tube in tube type fuel. These are called pressure tubes. And there are a fuel rods or the small yellow color ones, fuel rods. Around that you have heavy water, plain water, which is creates the pressure heated up, and you have heavy water for moderator to reducing, and you have control rods, control the reaction. And this water, whichever is heated up here, will be comes down like this and goes to here, and there is plain water comes and the water will be heated up. The heated water will be generating the steam goes. So the concept in all the cases is simple, where you have a nuclear reaction which gives a lot of energy, because this is exothermic reaction. The energy we are taking in different form just by immersing in water, water will heat up. If it goes to the second stage of, we will see the stages of Indian power program, but we see here we have another type of reactor called fast breeder reactors. Fast breeder reactors or breeder reactors. You see here, you have a reactor containment vessel where another vessel will be there. You kept the fuel over here. This is the core. The fuel was here. And your control rods are here. If you want, you can immerse it and remove. This fuel fully is, you can see, immersed in liquid sodium. Sodium is a metal, you know. It is a very soft metal, highly shining. You can even cut with knife, and all the chemistry people might have seen in their laboratories while doing experiments, sodium tests for ions analysis. So it is very dangerous. When it meets water, it gives exothermic reaction, produces hydrogen and a lot of heat. It needs to be handled carefully, but tons of sodium in a liquid form will be used in these type of reactors. What the main concept is, the sodium is heated now. Instead of water previously, now you have a sodium. Sodium will be heated now. The heated sodium comes over here. It goes to another loop. You can see here, outside is sodium. Inside tube you have water. Which water will be pumped here? That water gets heated up. The hot water goes to the, it is once again sodium, two sodium lines. Here is the water, sorry, this is the sodium, this is also sodium. This is inside reactor sodium, this is outside sodium. This sodium inside reactor is radioactive, and this outside does not have radioactive, because it is only a loop sodium, just comes and goes here. Because it is a heat removal. This sodium takes the heat from the reactor, and that sodium gives the heat to the water. You see here, there are a lot of technological advances required, because you have a place where water is inside the tube, outside you have sodium. If there is a leak, sodium water can mix, then it becomes explosives or like high heat generating. So you need to have better technology, better materials to avoid such reaction. Once again, the steam goes to the turbine, and the story is as simple. So mostly the reactors, most of the reactors works similar way, nuclear reactors. So we will see some points. People thought that nuclear reactors are not safe. Whether all the nuclear reactors are safe? 100% we can say that the nuclear reactors are safe. How? You can see this first picture where I showed a graph. Cumulative reactor years of operation multiplied by 1000. That is 15,000, 10,000, 5,000. So far from 1960s, the commercial reactors starting onwards up to now, it is 2010, beyond the 2017. Total cumulative years of operation of nuclear is around 17,000, 17,000. What is the reactor years of operation means? If one nuclear reactor works for 1 year, then it is called one reactor year of operation. Like that, so far the world, all the nuclear reactors have crossed 17,000 nuclear reactor of operation. Out of this 17,000 years of operation, nuclear reactor years of operation, you have 3 accidents. Should not have, but still, we unfortunately we had these accidents. The first one in 1980s, it is 3 Mile Island, and then Chernobyl, and recently it is Fukushima in Japan. Except that, we don't have any other issue so far in nuclear. And considering India, we does not have even a small accident so far. It is not that the technology we adapt is different, and so we can say nuclear power is safe means of generating electricity. Accident risks is low and it will be declining. It is declining and it will be declining. And in India point of view, if you can see, recently a 220 megawatt unit of India's indigenously developed. You see several reactors we are importing. So many are also developed in-house in India with collaborations between different units. That indigenously developed reactor Kaiga atomic power plant CAPS in Karnataka recently created a world record for continuous operation of 962 days. And the Tarapur atomic power station, that is CAPS 1 and 2, recently registered 50 years of safe operation in May 2019. So these numbers speaks about the safety of nuclear reactors. I hope you all agree with me. People also thought radiation is safe, is dangerous. Is radiation is safe? You see, whether we like or not, we are all exposed with radiation in all sorts. While listening to your mobile phones now, or from your laptops, or your desktop screens, you are getting some amount of radiation. From your homes, from the rocks, from the buildings, what we made with the rocks, cement, granite. And when we fly the aeroplane, you get more radiation. When you go to the hospital for X-rays, you get more radiation. Radiation occurs naturally, and we should not fear about it. We need to control it. We need to see that we should expose less for the radiation. We should be aware of it. Okay, anyhow, numbers will speak. The world average effective dose from background natural radiation, whether you are in a nuclear reactor, whether you are out of nuclear reactor, wherever it is, the world's natural background nuclear radiation is around 2.4 million millisieverts per year. That is acceptable. But many areas, their background radiation is so higher, 10 to 20 times higher than this 2.4 millisieverts per year. You can see Kerala, all the beaches, you can find out black, I will show sands where you have monazite sand, that is thorium. The natural radiation is around 12.5 millisieverts. And China, someplace, and Gaurapari, Brazil have radiations, background radiations are still higher, 10 to 20 times higher than the global average. Many of the building materials, cement, brick, stone, sand, granite, clay, fly ash, several things, they are all containing different elements, potassium, radium, thorium, and even granite contains uranium. They all give some amount of radiation. So every year nuclear medicine, and you see the radiation saves lives. DAE showed that in India how the radiation can be used for different purposes. It is treats several diseases like cancer, all your X-rays, PET scans, brachytherapy for cancer treatments. So all these are used, and even recently used for making highly resistant varieties of crops. So these are the ways nuclear or radiation helps us. This is a picture, you can even better understand that wherever you see these symbols, these are radiation precaution. Just like if you go to the X-ray or MRI, CT scan, you can find out these type of things. You see the standard radiation dose from clearance level is 10 microsieverts. We have discussed about 2.4 millisieverts, that is this value previously. This is the global average, natural radiation, which comes from, you will be getting the radiation even from ingestion, by eating some food, some vegetables, from that you may get. If you are traveling or from the space you will get. When you go high and high from the earth into the space by flying, you will be getting exposed to more cosmic radiation. On earth you will get some amount. So all these together you have 2.4 millisieverts or 2400 microsieverts per year. This is all. But if you can see here, X-ray scan, one X-ray scan each time you will get 50 microsieverts. Dose limit for police per year accepted is 1000 microsieverts. You can see here nuclear reactors, around nuclear reactors, it will be maintained that the total dose per year is around 50 microsieverts. The same you are getting when you go to the hospital and take one X-ray. So it is not that radiation is very dangerous, it is very safe. The thing we need to use in a proper way, and we need to contain ourselves. The thing is that how we can contain. One is you delay. For example, if you have a radioactive material, anything, you don't go nearer to that. You be away from it. That's why these symbols caution you when you are entering into a radiation thing. Where there is a radiation, be cautious. And you see, this is one high natural background radiation areas on Gaurapari, Brazil. You see the beaches, several people goes there for taking sand bath. So why they take the sand bath? You see the question asked to the couple, how do you feel in the sand? They said, we feel warm. We do not know the effect, but it's sure that it becomes warmer and warmer in the sand. We found something different from other places. What the something different? They get more radiation. They have more radiation in the sand. There is a radioactive elements. You see, these are the dosimeters which measures the radiation. They measured around this much. And in this particular area, it is a tourist place where you have hotels. They named after radioactive elements. Nevada, thorium hotel, radium hotel name like this. So average background radiation in this particular area you have very high, 400 millisieverts. It is a global average is just 2.4 millisieverts. That means the people are not living there. People lives there, and it is not much to them. People also think that the nuclear produces a lot of waste. I agree. It is not true for India. Because if you can consider this example, anyhow, you can just see total solidified high level waste, that is the waste at the end throughout, produced for generating electricity for consumption by an average Indian family for 25 years. The total waste generated is like this button. So far, the US is not reprocessed its fuel, I think. So the total, they might have generated the spent fuel, all can be put in one football stadium. So such a several years of reactor operations leads very small amount of waste. In India, it is not the case at all. Why we will see in our program talks. We adapt for a closed fuel cycle, what that means we will see. And we produce more fuel from the waste. And waste is actually a useful source for us. Recently, DIA developed a process to separate cesium-137 isotope from this waste and made it to pencils and given for the different blood blanks, where to purify the blood, sterilize the blood before giving it to the human body. People thought that nuclear power is too costly. The Electricity Board of India has given this table I took recently and notified on 2013. You can see that these are all nuclear power plants. The tariff in price per kilowatt hour, that is per 1 unit. You can see the 1 unit power mostly is 3.4 rupees final. But if you can see one reactor in India, Tarapur unit 1 and 2 sold at 0.94 paisa. Sometimes it's sold at 0.92 paisa per unit. And recently for coal-based power, and there is a bid, and where they quoted the power is around lowest is 3.26 per unit. If you compare with nuclear, they are even lesser than this. And it is not that when you go and build more nuclear reactors and you have more expertise in operating the nuclear reactors, it is sure that the power tariffs are tends to reduce with time in coming years. Another one is nuclear power is safe. Yes, already I showed the picture, but still if you can see some of the accidents, most worldwide severe accidents. Severe accidents of the scale is around 6, 7. You see you have only 2 severe accidents was listed by INSK. And if you can see the accidents from different power plants, the number of nuclear accidents is 1 and +2, but it is based on the severity, it was mentioned only 1 accident, that is which. Otherwise, the nuclear accidents are very less. accidents are very common, but it is not that nuclear also will have a lot of accidents. We need to control it, but still the accidents are very, very, very less. Now comes to the Indian nuclear power program. I may take some more 15 minutes. So the main agency responsible for producing nuclear energy in India is Atomic Energy Commission, under which Department of Atomic Energy. The Atomic Energy Commission was first set up in 1948 after just independence, and DA was later formed under this one. And DA's main vision, everyone should know that it should empower India through technology, creation of more wealth, and providing better quality life to citizens. DA is engaged in the design, construction, and operation of nuclear power reactors, at the same time research reactors, and support nuclear fuel cycle technology. In addition to that, DA also involves in societal benefit technologies. This picture may not be clear from your mobile phones or laptops, but it is can understand that points where you have DAE establishment in the India. All over India, we have DAE establishments, different ways. Some are the reactors, some are the research units, some of the mining places, some processing plants, some are reprocessing plants, some are research areas. Okay, all are around India. These are some numbers, may not be exactly perfect values, but India has around 70,000 tons of natural uranium deposits in our geological area. So the natural uranium deposits are very less when compared to the world. The concentrations of uranium also, as I told, it is very less. It is when compared to world grade, our uranium grade is very, very less. 8 reactors like Kaiga, Madras, MAPS, and Tarapur were using indigenous sources of uranium. That means the uranium which was explored from our geographical area, and within India it was produced. And remaining 14 reactors were using imported uranium. Most of them are enriched. India has reasonably assured resources of thorium. Thorium resources are used, I think, around 30% when compared to world thorium resources. But we can't able to use thorium right now. You see these beaches from Kerala, you can see the black sand, which is the monolith sand, which contains thorium. And in India, the uranium resources most comes from Jharkhand, 45% we found most. Then Andhra Pradesh recently also several places, so the increase is high. Then Meghalaya 16%, other states is. This is the Indian nuclear power program. As already in the introduction, Principal Madam explained that Indian nuclear power program 3 stage, which was the brainchild of Dr. Homi J. Baba in 1950s. And this one need to understand how India is putting its nuclear power program to sustain the production of electricity the years to come. The first stage where we are now is pressurized heavy water reactors. Because we have natural uranium, we no need to enrich, just put the natural uranium into the reactor and get the electricity whatever possible. After that, you have spent fuel where uranium is reduced now because the enrichment or enriched whatever normal uranium will be used. So you have the depleted uranium, and also you are producing plutonium in this reactor because the uranium 238, which takes the neutron, converts to plutonium 239. So this plutonium is now once again a fuel element. That's why this uranium and plutonium will be processed from this reactor, and you make sufficient amount of this. That's what is doing India right now. We are running several PHWs and getting all the fuel, and we have several reprocessing plants. I think mostly 3 places we have Tarapur and Kalpakam. We have reprocessing plants and reprocessing the fuel and getting the uranium and plutonium. And once that fuel is sufficient amount is there, then you give for the next reactors called fast breeder reactors. And India is having one fast breeder reactor, test reactor, which was working for the last 30 years. It is an experimental reactor, test reactor, where you are making the fuels in different compositions and irradiating in this and getting the power. Once you put this plutonium in this reactor, you see when you have a nuclear core where you put the plutonium fuel, it is getting neutrons comes and fission happens because of that lot of neutrons are there produces. These neutrons will escape. So around that, like a blanket, you put the thorium, which we have huge number in India, huge resources of thorium. Now this thorium you put around the nuclear core as a blanket, then what happens? The neutrons which escapes hits the thorium and makes into uranium-233. So in the reactor you are producing another fissile element called uranium-233. Now you have two fissile elements, even your plutonium is there, it is not fully used, and you have uranium-233. These can be reprocessed further. Your plutonium can be given back into this type of reactors, and uranium can be taken, and you go for the third stage, another type of reactors, advanced heavy water reactors, where the thorium which generated uranium-233 can be a fuel. You see now the fuel is U-233 isotope. That's why these reactors are called breeders, fast breeders. They produces fuel more than what they consume. That is called breeding. They utilizes the fuel and produces the energy at the same time. They produces more fuel. That fuel can be given here. These are really breeders. They also produces a lot of fuel because where once again you can use thorium as a blanket, and once again you get the thorium is converted to U-233. That can be processed and given back into the reactors, and you can continue the atom program to a large extent for producing more electricity. Since your thorium reserves are more, you can continue the program such a long time. But the key points here need to understand is the technology. How we are going to gain that. So India is around, well, these numbers already will be known, but right now India, the one thing about where I work is the Kalpakam Indira Gandhi Center for Atomic Research. It is a unique place in the world where we have the top 3 pictures, 1, 2, 3. These 3 reactors are exist in this center. We have PHWR maps, Madras Atomic Power Station 1 and 2, 2 reactors. And we have fast breeder test reactor. As I told, 30 years it is working right now. And another we constructed called prototype fast breeder test reactor. That is PFBR based on the same concept, breeder. And we have very small mini reactor, Kalpakam, commonly it is called Kalpakam mini reactor, where we are using uranium-233 as a fuel. It is just a test reactor which is used for neutron activation analysis right now. But the 3 reactors concept and the reactors are existing at IGCR Kalpakam. India's nuclear energy numbers, if you can see, as already Madam told, the operable reactors in India right now is 22 operable reactors, and the nuclear share of generation, total electricity generated in India, out of that, the 3.2% is nuclear share, very less, but still we are trying to go more and more. And recently, government has approved several nuclear reactors to construct, and reactors under construction is this. In January 2019, DA announced that India plans to build 21 new reactors, then increasing the combined capacity. So it is based on the time it comes up, and nuclear power currently contributes over 10%, and not a little higher number, it is maybe correct exactly around 10% world electricity production. And total number of reactors worldwide is around 442, because recently some reactors were shut down. So total we have, it is a recent report from, so where we have 442 reactors. You can see most of the reactors are PWRs, 300. So India's nuclear power program, we see in the first stage of Indian nuclear power program, we have PHWRs, I told already 22 reactors are there, all are first stage. And the second stage, we have this fast breeder test reactor. It is a sodium cooled fast breeder test reactor, indigenously developed by DAE and different institutes around the India, all over India. And we have another bit here, which is already its installed capacity is actually planned capacity 40 megawatt thermal. Recently it achieved 32 megawatt thermal for 33 years of operation. And we have another constructed fully, and it is advanced stage of commissioning. And recently it was mentioned that it will be commissioned fully or made critical or connected to the grid in the year 2022 October. This is called prototype fast breeder reactors. Once we have this 500 megawatt electrical, if you gain this, we really in the second stage of Indian power program, that is fast breeder reactors. Once you achieve sufficient control over the second stage of Indian power program, then we can move for the third stage. So nuclear fuel reprocessing, it is the main point for Indian nuclear power program, where we have a closed cycle. You see, there are two routes by which the spent fuel will be reprocessed. Just I may take some few more minutes. And one is, the first one is open cycle, where you use the fuel, and once utilization over, you can simply dispose it off. So several countries do this because they have more resources, so they can do it. And they will be just exploiting 2% of the uranium, not fully. But if you have a closed cycle, where you are trying to use that once used fuel, that is spent fuel, and get the useful products out of it, that elements, fuel elements, and can be once again used in the other type of reactors. Nuclear fuel reprocessing done in two processes. One is by using water-based aqueous reprocessing, another is non-aqueous, other than water. The main aim is just to get the useful fuel from the spent fuel. Spent fuel means once it is used. So aqueous based, where you have organic molecule like 3BP, tributyl phosphate, and endodecane. This is the solvent will be used for extracting the uranium and plutonium into the organic phase, then strip back into your aqueous, then go for the. I will show you one more picture where we can try to explain it a few minutes. And then you have a non-aqueous reprocessing, and India is the one now doing more research and concentrating, and IGCAR is the center where this particular pyrochemical reprocessing methods have been studied very well for the future fast reactor fuel reprocessing. You see, right now, India and worldwide, the most of the fuel used in the form of oxides. Where you know that oxide, the fuel fissile element density is less because it is oxide. More oxygen and your uranium is less. Only the uranium is undergoes the fission. But if I use a metallic fuel, directly it is more number of atoms of the metal is available. So you will get more energy density. But you have several other issues to take care. So that's why India is trying to go for the metal fuel based fast breeder reactors. Then we need to have a reprocessing methods. So this is the reprocessing method, pyrochemical reprocessing method, which can be used for metallic fuels. And now we have a bench, we have a laboratory level method developed already. And I can show. This is Purex process, just to understand the chemistry. Some few people, just 2 more slides, I will finish. You see now, this is the PHWR has given us fuel out. That is spent fuel. The fuel will be put in assembly, all those things. So you remove the assembly, everything, and chop it out, make it into small pieces. Put the in nitric acid. If you put the nitric acid, what will happen? The fuel UO2 base will be dissolved in them. The hulls, which the containing the UO2 fuel will be the hulls. They will be removed. They will not dissolve. If any gases are there, they will go out. Off gas treatment will be done separate. Once they are all dissolved in the nitric acid, that means I brought the fuel into nitric acid now, where you have plutonium nitric acid, uranium nitric acid, everything in the aqueous medium nitric acid, HNO2, correct? So now you do the clarification. There are some things, insolubles need to be removed. Then go for the preparation. That is, I require a concentration of particular range, like 3 molar or 6 molar. That will be done by called as preparation. Once you do the preparation, go for extraction. You might be seeing this extraction. Extraction is nothing but you separate the organic and aqueous. Correct? So you give TBP. It is a organic, and you have water-based nitric acid. Both are mixed together and shake well. Then what will happen? All the fuel elements from the nitric acid can go into the organic phase. Then from there you can separate uranium and plutonium different cycles, and you will get one side uranium oxide, other side plutonium oxide. These two can be given for the preparation of fuel and goes to the next type of reactor. And this is the last slide, pyrochemical reprocessing. As I told, it is for the metallic fuel. You see the concept here, there is no water involved. Clear? So I have a spent fuel which comes from the fast breeder reactors where the fuel will be plutonium, uranium, zirconium together. It is an alloy fuel. Uranium, plutonium are the fissile elements. Zirconium was added to increase the reactor temperature. You see, you will get more fission and you can get more heat output when you allow the fission to happen more and more. That means you have to increase the temperature of the reactor. If you are increasing the temperature of the reactor, your fuel should not melt. So the melting point of the fuel need to be increased. So for that purpose, the zirconium was also added. When you put these three together in the reactor, you get fission and you will be getting lot of whole period table elements will be formed. Lot of fission products. Minor actinides, sodium. Sodium is also one because all these fast breeder reactors, I told sodium is the coolant. So you remove the sodium, then go for the chopping and sodium removal. And then the main process is electrochemical electrorefining. Most of the people might be known this refining. From an impure metal to you get a pure metal. That is called refining, correct? So you take the impure, that means why it is impure the fuel? Because you have all other things. I don't require all these. Only I require uranium plutonium. So you do the refining, get the uranium and plutonium separate. Done. I have two cathodes and deposited uranium and plutonium. Take it out, then go for injection casting, make a fuel rods. This is the another plus fuel making process. This process works from different high temperatures. So the materials, all these are very, very important. But anyhow, this is the overview of Indian nuclear power program. And finally, one thing I need to tell because people also worries about this nuclear waste. You see the DAE, under the Atomic Energy Commission, there is a independent body called Atomic Energy Regulatory Body, AERB. Even nowadays, you might be seeing that if any X-ray unit or any scan unit is used in a hospital, they need to get permission from AERB certification because several times we have seen news there is a scrap which was thrown and it got radiation and even several people the radiation they were affected. So that's why all the radioactive elements using instruments comes under AERB. Even DAE comes under AERB. Most of the reactors are under AERB, even under IAEA. IAEA is the worldwide and AERB is within the. So the waste management philosophy is that no waste in any physical form is released to the environment unless the same should be cleared from AERB as per their regulations. So the main process philosophy which follows for the radioactive waste management worldwide or in India is you delay. Anywhere if someone asks, we never like to delay, but for the radioactivity it is better to delay. Instead of doing the work today, you just delay it for a year or now or something like that. So when you delay, what will happen? All the radionuclides, their half-life period will reduce and they will die. They will immediately reduce their radiation. So decay the short-lived radionuclides. Some are long-lived, you can't delay it. So, but short-lived can be done. And then if you have a huge amount of liquid, try to concentrate and reduce it, contain it. If you have a solid waste, you compress it. Contain activity as practicable, whatever the possible. Then if you have a concentration more, then dilute it and then disperse into a low level radioactivity. This is the way we can operate. So far we don't have in world, I think maybe in this year some facility may come for the geological repository for storing of the fuel. So far there is no storage because all the fuel which are used in the reactors in India is stored near to the reactor sometime, then it is taken for reprocessing. After reprocessing, you will be having very, very limited amount of waste that is called high level liquid waste that will be put into a glass matrix made into a glass, borosilicate glass or similar. There are different varieties people are trying. It is vitrified and put into the glass and put into this type of canister and close it and then go for the storage. This is about the nuclear. I hope I covered everything. So I agree. I hope this is the quote given by Homi Baba. Everyone should like that. If we never think that power is costly, because without power, no power is costlier than no power. So power, we require it. For everything we use this power. Even now we are running with power. So nuclear energy, I think everyone agrees with me that it is safe and environment friendly, and has seen the world wide nuclear track record says one of the best unparalleled safety is nuclear. Successful waste management and abundant fuel we have, and it is abundant, affordable, and greener. You may say that solar is good, wind is good, I agree, but still the capacity factor, if you can see, nuclear is highest, because once you construct the reactor and if you comes critically, it takes several years continuously works. This is the time the world needs nuclear power in particular. So if we can overcome our misconceptions, our understandings and about nuclear energy, then we can push the civilization into what I thought eco-friendly is or green is. Thank you very much.
Thank you, Dr. Jagadishwar Rao.
Thank you.
You have taken a wonderful topic and you have given a complete overview on the, I mean, you started with fission and fusion, and then you have discussed about the three-stage nuclear program. Then you have given some idea about the nuclear fuel cycle, the types of reactors, and of course, you have spoken about the risk of the reactors. I mean, how do the safety of reactors work? And then more importantly, is because a lot of waste gets generated from the nuclear reactors. The storage of waste, particularly the high-level waste, you have focused on that also. And of course, you have given a wonderful overview on the, I mean, information related to the nuclear reactor. I request now the participants if we can have one or two questions. But before that, let me put one point. If anyone has a question, please raise your hand or please type the question on the chat box because
that's okay.
Yeah, that will be better actually. Like if anyone want to have a question, please write the question in the chat box. And I request at this stage, please do not write other things on the chat box like thank you and all these things. It's kind request. In that process, we may miss the questions. So please raise your hand or you can type your question on the
Pradeep sir.
I welcome our second speaker. Sir is also ready. So if anyone has a question, please write it on the chat box.
Sorry for the interruption, sir. Is it audible, Pradeep sir?
Yeah, it's audible. Yes.
There is another instruction to all the participants. I can see some auto-generated names in the participants list. So all are requested to change their name as they have given in the registration form. So it will help us for certification purposes. So please do it. You can change your name by clicking on the participants, and at the top you will see your name. You can click on more, and then there will be an option to rename yourself. So please, all of you, please, those whose name is not clear, then they can write their names, original names. Thank you.
Okay, there is a question from Dr. Rao. I am just reading a question, and please, if you have answer, please try to answer that. Abhishek Panigrahi is writing that what can we do personally as a citizen to minimize the demerits of nuclear energy? As a citizen, does someone have some responsibility?
Okay. Actually, we need to understand the benefits of nuclear energy. And that's all what we can do. Personally, there is nothing. We need to support it. When it comes from, for example, India planning to have several nuclear reactors in several places. There are several hesitations because of the political or even the nearby villages. That when we have such things near to us, we need to enlighten them or make understand them what it is, nuclear, such that we are in a better way, indirectly.
Yeah, I too believe that as a citizen, the first responsibility should be let us understand whether it is good or bad. It's like something like some politician will come and say something and you will accept that. So rather than, I would say, being a person with science background, you should understand whether it is good or bad and you can have your own decision at the end rather than getting a biased decision from someone. Good or bad doesn't matter. I think as a citizen, that should be our responsibility.
Yes, yes.
Okay, Sachin Mishra is asking a question. Uranium fuel case is made up of which material?
Uranium fuel case.
Fuel case is made up of which material?
See, most of them are alloys, stainless steels, or in some cases we have a 9-chrome 1 moly. So these are based on the type of reactor, where it goes, and the fluence, how much heat it is generating, how much neutron flux, how many years it will be staying. But most of them are alloys.
Okay, thank you. There is another question from Vani Kima. Does reusing of fuel decreases its efficiency?
We never use the fuel as it is for reusing. We will be processing and we will make into 100% the same enrichment way as we previously used. Otherwise, we can't use. If any leftovers, we need to adjust the fuel composition. We will first adjust the fuel composition, then we will be using. And it is not that we are losing anything, because in a nuclear reactor, what we utilized is only 3 to 4%. Remaining so much is available. So we need to once again concentrate, enrich to the level what it requires. Otherwise, it will not undergo even fission. So we are not losing anything. We are gaining.
Can we go to slide number 15? Actually, Dr. C. Sanmugam from, I know personally, sir, from Anna University, he had some question in slide number 15. Sir says, inside the reactor, it is radioactive sodium, and outside it is non-radioactive. How is it possible?
You can see here, there is no direct contact of this sodium and this rhodium. The tube within that. If you still consider it is a radioactive, there is no problem. But still, you can see this is the one. I think my cursor is saying clear. So this red one is the one which is outside the tube. That is the one which goes to the reactor and comes here. So that contains purely radioactive. But the tube within that tube, which comes from the outside, this sodium, which is within the tube, there is no contact between them. The heat transfer happens through the tube metal, correct? So that's why there is no contact with the radioactivity.
Okay, can we do one thing? Is because there are so many questions people are asking. So I would rather say, like, because the second speaker is also ready and we have some constraint on time. So we will share the email ID of Dr. Jagadishwar Rao, and whoever is having some question, maybe you can ask them, and in his free time, he will try to answer all the questions. Personally, I know Dr. Jagadishwar Rao, he will not hesitate. In his free time, I'm sure he will respond to that, because there are, I can see at least some 30-40 questions already. So I'm sorry, participants. I will provide the email IDs so that you will get your answer certainly.
Thank you, Ananda. Thank you.
Thank you. Thank you, Dr. Jagadishwar Rao, for your wonderful presentation. So practically, it is not possible to unmute everyone to give a round of applause, but on behalf of everyone, I applaud from my side. And now I request Dr. M.V. Ramana to take over from this point. And I welcome you, sir, to this webinar. And it's a pleasure, it's an honor to have a person of your caliber in our webinar for a place like, for a remote place like Rayagada Autonomous College in a state, Odisha. I give a brief introduction about Dr. M.V. Ramana. Dr. Ramana is the Simon Chair in Disarmament, Global and Human Security, and Director of Liu Institute of Global Issues at the School of Public Policy and Global Affairs, University of British Columbia in Canada. He is the author of The Power of Promise, Examining Nuclear Energy in India, which is a Penguin book publication published in 2012. And he is the co-editor of Prisoners of Nuclear Dream, in publication Orient Longman in 2003. Ramana is a member of the International Panel of Fissile Materials, the Canadian POGWAS Group, the International Nuclear Risk Assessment Group, and the team that produces the annual World Nuclear Industry Status Report. He is the recipient of a prestigious Guggenheim Fellowship and a Leo Szilard Award from the American Physical Society. With this brief introduction, I request Dr. M.V. Ramana to take over.
Thank you very much. I really appreciate this opportunity to talk to you all, and I'm deeply grateful to be invited to speak to you. It's a very important topic to think about nuclear energy and to consider it very, very carefully in light of all the many points that Dr. Rao has already outlined. I think what you will find is that we agree on a lot of the factual details. We just probably will interpret them very differently. So here it is that I'm going to offer my kind of what you characterize as misconceptions about nuclear energy, which I think are the right conceptions. So let me just start. So let me start by first sort of explaining what the global picture on nuclear energy is before I move to India specifically. So around the world, there are about 400 reactors operating. And this capacity has grown over the last about 60 years. Many of the reactors were constructed during the 1970s and 1980s. And then since the 1980s, it has been more or less flat. So if you look at reactor constructions, the construction sort of happened mostly in two big waves. One wave sort of peaking in the 1970s, which was mostly in the United States, and then one in the 1980s that focused mostly on Western Europe and the rest of the world. After roughly around 1985, you will see a very clear declining trend. And that is, I will sort of explain why that is later on. But since then, what you will observe is that there are many years when there are more reactors that are being shut down than actually are being constructed. I just want to check, by the way, are you able to see the different slides? Is my slides moving properly for you?
Yeah, we are able to see exactly what you are presenting. Thank you.
Just wanted to make sure. Thank you. So you'll see that there are some years when there are more reactors shut down than actually starting up. And there are at the moment around 50 reactors under construction, but the construction is something which does not necessarily guarantee that the reactor will be completed. Of around 50 reactors, 48 to be precise, where reactors whose construction started and proceeded to some extent, and then the agencies that were constructing the reactor, for one reason or the other, decided to suspend or abandon the reactor construction. In some cases, there were even reactors that were fueled completely, including a fast breeder reactor in Germany in a place called Kalkar. Essentially, the developer of the reactor decided that it was not worth operating the reactor. And it was subsequently sold to somebody who used it as a theme park for people to go and have fun. The reactors take a long time to construct. So if you look at the reactors that started up in the last decade, the average weighted construction time that I have calculated based on data from the International Atomic Energy Agency is around 99 months. In other words, close to 9 years, 8 to 9 years. In some cases, it could be much longer. So the prototype fast breeder reactor that Dr. Rao talked about, the construction of it started in 2004. We don't know when exactly it is going to actually be start operating, maybe by 2022. So you can see it's taken about 18 years to construct, even if everything goes well at this point. So if you want to think about a new reactor being constructed, you have to give it something like 10, 20 years before it can actually start generating any electricity. So this is a very slow process, and this I think has implications for how we think about using this source of energy if we were to decide to do that to try and mitigate climate change. I'll come back to that later. The result of the fact that this construction is very slow and that there's the construction has generally stopped after the nuclear energy has been declining consistently. The maximum it ever was in 1996 when it was 17.6%. And since then, it has declined almost consistently and it's now around 10%, right? So just think of it this way. Only about 10% of all the electricity that's generated around the world is coming from nuclear energy, right? And this fraction, as I mentioned, has been declining. So in other words, nuclear energy is not a growing source of power, but a declining source of power. And the International Atomic Energy Agency, an agency that is dedicated to promoting nuclear power, every year produces projections for how much nuclear power they think they will be operating in 2030 and in 2050. And what you can see here are my plot of what they have been projecting. And what you see is that there's again a continuous declining trend. That, in other words, even the most optimistic agency, the agency which is in charge of promoting nuclear power around the world, does not think that nuclear energy's fortunes are very good. The one thing which I want to mention is that in these projections, even in the most optimistic scenarios, the purple bars that you see, the share of electricity at that point will be at best around 10%. In other words, nuclear power can at best, if everything goes well, if it's very optimistic, then you can say it can maintain market share, with 10% of the electricity. In all likelihood, it is going to go down quite a bit from what it is now. Why is this trend? The main reason is very simple. Nuclear power is not economically competitive, right? And the main reason for why it is not economically competitive is that reactors cost too much to build. So here's a plot of what are the costs of construction and costs of generating electricity from different sources of electricity in the United States. This is produced by a financial company called Lazard, and they do this every year. And what you see is that on the leftmost column is nuclear energy and its cost of construction, which means how much you have to spend to generate each kilowatt of electricity or each megawatt of electricity, and the cost of generating each unit of electricity, in other words, each kilowatt hour of each megawatt hour, are the highest possible among all possible sources. In comparison to that, the cost of generating solar energy is about, it's the cost of construction of solar energy or wind energy is about a factor of 10 smaller, right? And the cost of generating electricity from those things is about a factor of 6 smaller. Another problem with financial problem is that you can take it as given that whenever people, scientists and engineers who come up with these designs make a cost estimate, you can be sure that it's going to be higher, right? In every country, there has been cost increases. One study found that 175 out of 180 nuclear projects had cost increases and also time of construction. And I give you the example of the prototype fast breeder reactor. It was supposed to have been constructed in 6 years, and with luck, we can have it being constructed within 18 years. And the cost is also nearly doubled at this point. And I'll come back to that point. And this is not true only with the prototype fast breeder reactor. It happened in Kudankulam. It is happening in the United States, in France, in Finland, in Russia, everywhere you can see. Unlike every other source of energy, things like wind and solar, which have come down in cost tremendously as you have more and more construction, nuclear energy is very different. Its costs actually have increased over time. In the 2 countries where they have had the most experience with building nuclear plants, namely France and the United States, this is the plot on the left side is the construction cost per unit of generation capacity. And you can see that in both those cases, as time increased, as time proceeded, the cost of nuclear power went up. And one way to understand why this is actually happening is that as you get more experience with building nuclear power plants, you actually realize there are more and more safety challenges. And when you try to fix some of these accident risks, then the cost is going to go up. In contrast, with things like wind and solar, as you gain experience, you understand how to do things more efficiently, and that is reducing the cost. And in the United States and in Sweden and in various other countries in Western Europe, where they have a competitive electricity market, unlike in India, where the cost of electricity is fixed by a regulatory authority, like the Central Electricity Authority or some state electricity board, if you're operating in a marketplace and every source of electricity has a chance to compete for the available demand, what you find is that nuclear power plants have been shutting down in recent years because just the cost of running, not just building new nuclear plants, but just operating an existing plant turns out to be more expensive than building a new solar or wind or even natural gas plant. This has resulted in some largest companies involved in nuclear power around the world either filing for bankruptcy. This is the case with Westinghouse, the company that is supposed to be producing the AP1000 reactor that was planned for construction in India, in Andhra Pradesh, in a location called Kovada. This is the result of the so-called US-India nuclear deal. And also companies that are producing uranium have had record losses in the last several years. The other aspect of the financing or the economics of nuclear power is that there are long-term costs, costs that are going to be incurred way down in the future, well after the nuclear reactor has stopped generating electricity and producing any kind of revenue for the person who's the organization that's operating the plant. And often those costs, because they are underestimated routinely, they tend to go to the taxpayer. So this is an example from the British energy minister saying they are spending about £2 billion a year to just cleaning up what he called this mess. All right. And these are not people who are opposed to nuclear power. These are just people who are concerned about having to pay these high costs. By the way, I'm happy to share these slides later on if anybody is interested in seeing the details. I know I'm walking through this pretty fast, but I'm happy to also answer questions later on. So now I'll turn a little bit to what's the situation in India before I go to discuss some of the challenges or the problems with nuclear energy. So in India, we already heard has sort of several nuclear plants and other nuclear facilities. Their installed capacity is about 6,800 megawatts. And there's one pilot scale fast breeder test reactor that Dr. Rao spoke about. And there are a number of reactors under construction, including reactors that are being imported from Russia, that are being constructed in Kudankulam, heavy water reactors in Ravandhata and in Kakadapar, and this one prototype fast breeder reactor in Kalpak. If you look at India's share of installed capacity, then nuclear power is less than 2% of all the installed capacity in the country. And this is after nearly 70 years of trying to operate nuclear reactors. Right? The Atomic Energy Commission was set up in 1948, and the Department of Atomic Energy was set up in 1954. And the first reactor, the Apsara, was started functioning in 1956. So this is a very long history to be able to generate only less than 2% of the installed capacity. And if you look at the share of actual electricity production, it ranges about 3% typically. Some years a little bit higher, some years is a little bit lower, but it's roughly around 3%. And what you see in last few years is that the production from the relatively new sources of electricity that we've seen in the country, wind and solar, have exceeded nuclear power. Wind has exceeded it since around 2012, and solar exceeded it for the first time last year in 2019. And the trends are that wind and solar will quickly will overtake nuclear and leave nuclear behind quite a lot. So in terms of trying to ask the question, yes, India has a large shortage of power. What can we do about it? It's very clear that, there are some sources which are cheaper, which are faster, and which are cleaner, and those are the ones to be emphasized on. In coming back to nuclear power, there has been, despite nuclear power's small share, there's been no dearth of sort of long-term plans which envision a very large expansion of nuclear energy. So this, for example, is one of the early major projections made in around 1970, and they talked about nuclear power growing to about 43,000 megawatts by the end of the 20th century. And the actual capacity in 2000 was about 5% of what was projected by the Atomic Energy Commission. And this trend continues. So why is this trend? This happened in 2000, and now in 2020, for a long time, they were saying there'll be 20,000 megawatts of generation capacity. As I mentioned earlier, we have only about 6,800 megawatts of capacity. So nuclear energy has never met any of the promises that it has made. But why is this? Well, there are sort of multiple reasons. The first, as I've sort of already mentioned, is that all reactors that have been constructed in India have had overruns in construction time and in cost. It's always taken them longer and has been more expensive than they have projected. And an important reason is that problems that had not been envisioned when the site was selected for the construction had not been envisioned earlier. And so unexpected problems have always arisen, and there is no reason to expect that in the future they will be able to foresee all problems that are going to come up, right? And secondly, when they make plans, they do not allow enough time to learn from the lessons of earlier failures. So this is going to be a problem with the prototype fast breeder reactor. The Department of Atomic Energy is already talking about building 2 more such things when they should have realized that the first the first demonstration plant they're building is already so behind in schedule, has had numerous problems, that they should try to understand why these problems are occurring and whether they should even repeat that experiment again. Another problem has been that they have had a multiplicity of designs, so you're trying to learn very many different kinds of technologies, and that's not conducive to sort of fast growth of any kind of technology. Unlike in, let's say, wind turbines or solar panels, where you're basically remanufacturing the same design again and again, and therefore you can learn from that experience. There are other issues. There is opposition in almost every case since the 1980s. So all new reactor projects, all uranium mining projects since the 1980s have had substantial public opposition, and I will explain to you later on why I think this opposition is very highly justified. And I think there are concerns about radiation, about accidents, as well as livelihood, because nuclear reactors will compete with farmers and fisher people for water, for land, and so on and so forth, and this is only going to intensify with time. As I mentioned, the Department of Atomic Energy is never short of making up future plans. So in 2008, the chair of the Atomic Energy Commission projected this future where he thought nuclear energy was going to increase by a huge factor by the mid-century. And this is going to be fueled by 2 kinds of reactors, so-called breeder reactors that Dr. Rao talked about, and I'll talk about that too, as well as reactors that were to be imported from the West. And I'll talk briefly about that as well. So this is what the projection has been, and there is no doubt in my mind, and should be no doubt in your mind also, that this is not going to happen, right? The past history and a whole bunch of problems that I'm going to explain will make it sure that this is not going to happen. And we've already, Dr. Rao thankfully has already talked about the 3-phase plan, so I'm not going to explain that, but I'm going to focus on the second phase, namely breeder reactors. The breeder reactors are things which were envisioned way back in the 1950s around the world. Bhabha was not the only person to be enamored about breeder reactors. There's a lot of physicists and scientists who were thinking about it. But as countries started constructing them and spending very large amounts of money and research and development on them, they thought that they discovered that there were lots of problems with breeder reactors, right? And therefore, despite the fact that countries have spent billions of dollars, many of the Western countries, including the United States, France, the UK, and so on, have essentially given up on breeder reactors, right? So the pursuit of these kind of reactors, this technology, is, I think, not learning again the lessons from all these other countries, right? And there are basically two main sets of problems with breeder reactors, including the fact that they're very high cost, which I've sort of talked about generically with respect to nuclear power. In the case of breeder reactors, there's a very sensitive dependence on the fuel chain. In other words, in order to produce the fuel, you have to do this reprocessing process, which I'll talk about later, which is an extremely expensive and messy process, very chemically very dirty process, and prone to lots of failures. And likewise, breeder reactors themselves have had a lot of operational and safety issues, which I will describe. This is why I think many countries have essentially given up on breeder reactors. So if you look at breeder reactor performance, most reactors which have been operated around the world have had very poor levels of performance. So the first table there shows what's called the cumulative load factor, which is the fraction of electricity it could have produced. The fraction of electricity it did produce to the fraction of electricity it could have produced. And you see that most of them have really not operated well. The one exception is the Russian BM600, which has had a number of problems. And I think the way it has been operated, as you can see in the second table, is that it has been operated many times when there were ongoing accidents, including fires and so on, which I think is not good safety practice. And part of the reason why performance has been very poor in breeder reactors is that for the reason that Dr. Rao mentioned, which is that they use molten sodium, liquid sodium. And again, from your chemistry classes, you know that sodium is actually a very difficult material to deal with. It does not react well with air, it does not react well with water, it can explode, it can start fires, and you've seen all of those things in breeder reactors, right? Including at the fast breeder test reactor. So that's one reason why reactors have operated very poorly. In the case of the fast breeder test reactor, for example, it was approved in 1971, supposed to start operating in 1976. It started operating only in 1993, essentially. There have been numerous small accidents, sodium leaks, assembly breakage, unexpected reactivity transients, etc. It took 15 years before the reactor could even manage 50 days of continuous operation. It could be shut down all the time. And during the first 20 years, it had less than 20% availability factor, which means only about 1/5 of the time was actually operating. The rest of the time was shut down. Now, coming to the fast breeder, the prototype fast breeder reactor, if and when it operates, even with the most optimistic assumptions, these were the cost calculations that my former colleague Suchitra and I made, which showed that, with the initial expectation of what the cost was going to be, and comparing it with heavy water reactors, which is the mainstay of the Indian nuclear fleet, we found that the prototype fast breeder reactor would generate electricity at something like 80% more expensive. This was with the original cost. Now the cost of the prototype fast breeder reactor has nearly doubled. And so this difference in cost is going to have gone up only higher. In other words, the prototype fast breeder reactor, if and when it generates electricity, will be generating electricity, which is very expensive, right? And so when you're feeding that into the grid, you're going to only increase the cost of power to consumers and to the taxpayer. The other alternative, and so because of these two reasons, one, the fact that reactors are not operating, the breeder reactors are not operating well and they've had numerous problems, and because they are so expensive, we should not expect to see a large growth in breeder reactors. So if you go back to the projection made by Kakodkar, the big sort of fast breeder block that's sort of seen on the top two are not going to actually materialize. The other option that people have talked about is importing reactors. And again, there's the same problem. So in the case of the Jaitapur reactor, the reactors that were to be imported from France, the EPRs, my friend Subrat Raju and I calculated, and we published this in Economic and Political Weekly, that the cost of power from this can be somewhere between 15 to 25 rupees per unit, depending on what the cost of the reactor actually turns out to be. And you must have all seen that in today, if you look at auctions for solar energy and so on, the cost of electricity from those is around 2 rupees 50 paise, 2 rupees 70 paise, things of the sort. And by the time Jaitapur, if it is ever constructed, comes online, you can be sure that the cost will have gone up further to maybe under 2 rupees. So the cost of power from Jaitapur will be a factor of 10 larger than any alternative that you have. So in other words, again, you're sort of, if you build this, you are guaranteeing that people will be paying higher cost for electricity when there are much cheaper and better sources available. Finally, there's another issue which came up with respect to these imported reactors. When reactor vendors from countries from, vendors from other countries like the United States and France started thinking about selling reactors to India, they demanded that India shield them from any liability claims. In other words, if there is an accident, then people in India will not be allowed to claim compensation from the reactor vendor in case the accident has happened because of a problem with the reactor. So this is sort of like what happened in the case of Bhopal, where Union Carbide, now Dow Chemicals, essentially went scot-free. They paid a very small amount for the cost of the accident. And one would not like to see that repeated. This demand from vendors was sort of taken up in the Indian Parliament, and there was a big debate around 2010, the Indian Parliament ended up passing a law where the liability for an accident ended up being capped, meaning the maximum liability that the operator, in this case Nuclear Power Corporation of India, would be paying to people who are suffering from an accident would be so much smaller than the actual cost of the accident. So just to put that in perspective, the cost of dealing with Fukushima has been estimated somewhere between $200 billion and $700 billion, right? Whereas here you're talking about capping these levels at a level that's far lower than that, okay? And both of these liability caps and shielding the vendors will actually end up in vendors and operators sort of not caring so much about safety. The connection to safety is that the resistance on the part of the vendors to accept liability is basically saying that they are themselves not confident that the safety of the reactor is guaranteed. If they're really confident accidents are not going to happen, they should say, no problem. We will pay any compensation that is required. Because I know that my reactor is never going to have an accident. But actually, when it comes to putting money on this, they refuse to do that, right? And so the question really you should be asking is, if the nuclear companies are willing to stake their financial health on these claims of 100% safety and so on, how can the government ask local residents in Kudankulam or in Kovada or any of these places to risk their lives? Okay, so to recap what I wanted to say about nuclear power in India, India will not meet any of its ambitious goals for nuclear power because of the reliance on builder reactors, which I have explained to you are very problematic designs and very expensive designs, and plans for importing expensive designs. And these plans have been made up with no lessons learned from history, either Indian or global. So there was an old quote from an economist in MIT called I.M.D. Little in 1958, where he said, Dr. Rao sort of quoted Bhabha, and I think Bhabha was right in saying electricity is in short supply and we need power. But if you're going to keep spending money on a source of power which is more expensive, and at that time it was twice as expensive, now I've told you that's about 10 times as expensive in some cases, then obviously it is not going to be a good way to try and deal with electricity shortages in India. So it's going to continue if you focus on nuclear power. Okay, Let me now turn to some of the other challenges, or I would characterize them as problems. Challenges is the word that the organizers used in describing the session for nuclear power. The first, I mean, again, we've talked about it, but let me just briefly explain why I think these are severe problems. The first is that nuclear energy is capable of severe accidents. We've sort of talked about that. And this is a very unique feature. And the reason is that this is the only source of energy where the damage from the accident spreads out in space and in time. So here, for example, is a map of the area around the Chernobyl reactor, which blew up in 1986 in Ukraine. And the red parts in red are those areas which have high levels of radioactive contamination. And that contamination persists till today, now 35 years nearly after the accident. And there are still parts where people cannot go to live because the levels of accident, the levels of radiation are so high. In other words, this is going to take decades to clean up or to be able to be inhabited. And so it spreads out over time. And as well as you can see the scale of this distance, the hundreds of kilometers. In fact, every country in the Northern Hemisphere, including India, received some radioactive fallout from the Chernobyl accident. No other source of energy has this feature. And governments routinely discount the likelihood of accidents. After the Fukushima accident, these are governments which have interest in promoting nuclear energy. The British government, for example, internal emails were leaked to the Guardian newspaper, which showed how the government was planning to confuse people and tell them there's no risk of Fukushima in UK and so on and so forth, right? And officials, unfortunately, who should know better, scientists, try to support this. So after Fukushima in India, we saw a number of statements by heads of the Atomic Energy Commission and so on, saying nuclear reactors are 100% safe, they cannot happen in India. These are not scientifically tenable arguments. Right? The best thing you can say is that the risk is low, but that's not saying, it does not mean that it is safe, that it can never happen, right? And so this is a huge problem. And unofficial death estimates are underestimated deliberately and systematically. A recent book by Kate Brown at MIT has documented this in great detail in the case of Chernobyl, about how official agencies like the International Atomic Energy Agency routinely underestimated the number of deaths, the number of cancers, and so on and so forth. As an aside, can reactors be made safe and accident-proof? And I'm going to try to explain why it is very difficult. So nuclear reactors are very complex technologies, as you must have seen in the graphs, the pictures that Dr. Rao sort of showed. There are lots of things going on inside those reactors. You know, sodium that is circulating at very high temperature. It's very corrosive. It has lots of problems with exposure to water and so on. It's operating at high temperature. And if there is an accident, large energy releases are possible. And events in the case of an accident occur at a very rapid pace. In the case of Chernobyl, there was about 1.5 minutes between the first warning and the first explosion. Really no time for an operator to be able to do much. And secondly, a number of people who study the operations of reactors and other complicated technologies suggest that there are properties of these technologies that make it impossible to stop accidents. In particular, a sociologist called Charles Perrow identified two fundamental features. One he called interactive complexity and one he called tight coupling. And the argument he made was that these are essential features in nuclear reactors. You can try to make reactors less tightly coupled, for example, but that will mean a higher cost. So because of cost-cutting priorities, these features are built into nuclear reactors. And when these features are present, there will always be the possibility of an accident. You can never rule it out, because the reason is that you can never make sure that you know all possible ways by which an accident can happen. And therefore, when scientists and engineers try to project some kind of an estimate for how, what the likelihood of an accident is, what the probability of an accident is, those are completely misleading. Because this is what happened in the case of Fukushima, where they misestimated the likelihood of a tsunami, for example. And the kind of ways by which people try to protect these kind of accidents makes it more expensive, but also can make things worse in some cases. other problems with it. There's routinely overconfidence by nuclear authorities. I mentioned to you the case of the statements by the Atomic Energy Commission chair after Fukushima. In another statement, he said the probability of an accident is 1 in infinity, in other words, it's 0. And that I think is a completely wrong way to look at accidents. And this shows a kind of overconfidence, which then is going to translate to operational carelessness in various ways. And we have sort of documented this in great detail in the case of India in a paper in Journal of Research. In another paper, we showed that the regulators who are supposed to be the Atomic Energy Regulatory Board that Dr. Rao talked about, which is supposed to be an independent agency, ends up actually not doing its duty because it's unable to actually regulate this carefully for various reasons which we have explained in that paper. The best example of trying to understand this is in the case of the prototype fast breeder reactor, where this particular reactor design is capable of a certain kind of accident called a core disassembly accident. Such an accident is not possible in heavy water reactors, and this has to do with the fact that the reactivity of the core will change in certain ways, it will increase if the core gets rearranged. And what you find is that the possible amounts of energy that are released in the event of an accident can be extremely large. There will be an explosive release of energy, and that will not be contained by any kind of containment design. So in the case of the prototype fast breeder reactor, what the the IGCAR, the Indira Gandhi Center for Atomic Research, and BAE have done is underestimated what the amount of energy that can be released, and therefore has made a containment design that will be inadequate. So in the event of an accident, the containment of the prototype fast breeder reactor will likely fail and radioactivity will be released. There are also many other evidences. There have been numerous accidents. In this case, I actually beg to differ from Dr. Rao. There have been a number of accidents in India, and these are only the accidents that we know about in public. There may be other things we don't have knowledge about. We have to rely on whatever is released through newspapers. There's a lot of other things which happen inside, which we don't have access to. And there are a number of accidents have happened, including at Kalpakam, in Kaiga, in Katnapar, and in Narora. And in the case of Narora, which is in Uttar Pradesh, this was the accident that happened in 1993, which came closest to a large radioactive release. And this happened because some blades in the turbine generator snapped and set off a fire that burnt a whole bunch of systems. And the problem is not just that it happened, but it was completely avoidable, because this problem had been identified earlier by General Electric Company, and the authorities did not take into account this. And there was a similar fire in Kakrapar reactor and earlier one in Rajasthan, which didn't actually result in the kind of safety changes that had to be done. And so in bottom line, I think there are a number of problems with the way reactors are operated in India, and you cannot rule out an accident. The bottom line, again, for globally also, is that the probability of an accident in a nuclear power plant is uncertain and is certainly greater than 0. So there's no such thing for safe nuclear power. Second problem is that nuclear energy is closely linked to nuclear weapons. This is because all nuclear plants involve the use and production of enriched uranium or the production of plutonium, and even small nuclear power plants, in other words, which produce a small amount of electricity, can produce enough weapons-grade material to produce about 10 nuclear weapons. So this is a huge problem, and all kinds of plutonium can be used to make nuclear weapons. And because all nuclear reactors produce these or are fueled by these, as in the case of the prototype fast breeder reactor, all of these can be used to make nuclear weapons. And it's impossible to sort of make sure that none of this has been removed, especially when you do reprocessing. And we have sort of calculated in the case of prototype fast breeder reactor, you can produce about 125 weapons from just the core of the material there. And in most countries, there's a close relationship between institutions that work on nuclear power and nuclear weapons. This is certainly the case with the Department of Atomic Energy, which has tried to use its ability to produce nuclear weapons to allow it to subsidize its capacity to make nuclear energy, and vice versa. and essentially making a series of promises that it can never deliver on. So again, the bottom line is that nuclear power capacity means some nuclear weapon capability. And if you're thinking about nuclear power globally, that's definitely not a good thing if you want to have the spread of nuclear weapons. But the third problem is that nuclear power produces radioactive waste that remains hazardous for thousands and thousands and thousands of years. So we've already, Dr. Rao has explained all that. So I'm not going to sort of go through it in great detail. Just to say that the method that India uses for reprocessing, which involves chemical processing of the fuel to separate out the plutonium and uranium in it from other waste components, produces a huge amount of different kinds of waste. Low-level waste, which is actually discharged into the environment, usually the sea in the case of India, because all of India's reprocessing plants are either on the Arabian Sea or the Bay of Bengal, and intermediate high-level waste that have to be disposed of eventually. The low-level waste that is being released results in radioactivity being spread over very large areas. So these are, for example, graphs of radioactive materials like liquid tritium and technetium found in seawater in areas around reprocessing plants. So Le Havre is in France, Sellafield is in the UK, and Ireland actually challenged the UK about operating one of these things. Okay, so that's the sort of low-level waste which we are all being subject to at some level, because if you eat fish from the ocean, for example, then there is a certain amount of radioactivity that's coming from reprocessing plants. Coming back to sort of higher level waste which is stored, what do you do with it? People have explored various options to do with it, but essentially the problem is that most people have agreed that we should build a deep geological disposal site, a repository somewhere. It's just a fancy way of saying you dig a deep hole somewhere and bury it there, right? And you hope for the best. The problem is that any repository will eventually be compromised, typically by water, and radionuclides will escape into the biosphere. Why is this the case? Because the radioactivity of the spent fuel will last for something between 100,000 and 1,000,000 years, right? It is impossible to guarantee that any repository based on any kind of material will actually hold for that long a period, because you have to think about all kinds of geological changes, all kinds of chemical changes, all kinds of physical changes which are happening inside the repository. And so the result is that nowhere in the world has there actually a demonstrated solution. There is no operating nuclear waste repository anywhere in the world for commercial spent fuel. There is one repository for certain kinds of waste that came out of the US nuclear weapons program in New Mexico in a facility called Waste Isolation Pilot Plant. And in 2014, that had a very expensive accident involving an explosion, which happened like 15 years after location was commissioned. And this was a facility that was supposed to protect the waste for 10,000 years. So clearly, the scientists didn't expect all kinds of accidents, which kind of proved the point which I made earlier, that these are very difficult to predict what's going to happen. So accidents, even in the case of waste repositories, are kind of inevitable. They'll happen sooner or later. And the ethical challenge here is that you're producing certain kinds of radioactive waste that have to be held away from human beings, because this is very dangerous to human beings, for hundreds of thousands of years. And there is nothing in human history that is comparable to it. And you should think about this as an intergenerational equity question, that we use the electricity, some future generation will have to bear the risk of potential exposure. It could be our grandchildren, our grandchildren's grandchildren, and so on and so forth, way, way, way in the future. And also think about this concept problem with it, which is that how do you, even if you find a repository, how are you going to tell people who are living, let's say, 10,000 years in the future or 20,000 years in the future, that this particular location has some radioactive waste in it? The oldest writing we know is about 5,000, 6,000 years old, right? And so how do you tell people? This is a huge challenge. Nobody really has a good answer for this. So the simplest answer which you can say is that when you know you're producing this really difficult material to deal with, the first thing you should do is to stop producing more of it. Nuclear power also has very unfavorable public opinion. It's considered to be the most difficult technological hazard. People are rightfully, I think, concerned about the risk that it poses. Scientists, social scientists who studied it have pointed out how it's why it's so special. And this is why routinely in public polls in many, many countries, it rates very, very low. And we also see protests. We have seen it in the case of India, in the case of Kudankulam, for example, and other places, that, when there are accidents, when there are events, people come out in large numbers and say, we don't want any more nuclear power. And often the way that actually this is dealt with, this kind of protest, this kind of expression of democratic opinion, is that the governments typically just basically stop them. They kind of don't listen to the voice of the people, which is a violation of democracy in a way. And when people say, there's risk everywhere, we all have to make some of these choices, the problem is that some people do the risking and some people do the choosing. People in Delhi, people in Washington make the decisions, but it's people who are far away from them, who are very disempowered, who don't have political representation, who are the ones who are going to suffer the consequences in the event of an accident. So again, this is a huge democratic challenge, right? So let me sort of end with just a couple of points. Much of the discussion today is in the context of whether we should expand nuclear power to solve climate change. And I would argue that this is not a desirable solution for the reasons that I mentioned, that if you were to expand nuclear power, you're going to have an increased risk of accidents, which means that certain people in those areas might have to leave those areas and never come back. Imagine that there's a nuclear plant near your house and there's an accident, and you're told you have 24 hours to leave your house because there's going to be radioactive contamination. Take what you want. You can never come back for the rest of your life. How would that feel, right? That's the kind of choice that many people who are near nuclear plants are being faced with. They are of course told that no accident will happen, but as I have argued earlier, accidents are essentially inevitable. They're not going to happen every day. They're not going to happen every month, but sooner or later, accidents will happen somewhere or the other. The second is that power and weapons are closely linked. And so if from an ethical point of view, we think nuclear weapons should not be present, then we should also be thinking about not having nuclear power. And lastly, nuclear power also produces these radioactive waste that are hazardous to human health, that have to be kept away from human beings for hundreds of thousands of years. And this is, I think, a very difficult ethical dilemma that we should not be having to confront in order to solve climate change, especially because there are other alternatives. The other set of arguments about nuclear power and climate change is that even if you were to say, look, climate change is such a big problem that we have to face some of these risks associated with nuclear power, the problem is that it is not going to be feasible. I already argued to you that nuclear power is actually declining in share of electricity. If you were to think about nuclear power as a solution to climate change, it has to expand and take over a lot of the share that is now held by fossil fuels. That's not going to happen. Secondly, it's not going to happen primarily because nuclear power is very expensive. So you're paying 10 times as much to produce electricity or to construct the plant. Then obviously it's not a good way to deal with climate change because you're spending 10 times to deal with the problem. Then you can deal with it for a much smaller fraction of the cost. The second reason is that nuclear power plants take such a long time to construct, and agencies like the Intergovernmental Panel on Climate Change tell us we don't have a lot of time. In fact, if you look at the 2018 report on 1.5 degrees Celsius, from the special report on 1.5 degrees Celsius, the IPCC argued that we should reduce our emissions by 50% by 2030, right? That's not the time frame when you can imagine even nuclear power sort of expanding by a small fraction of what you have to do, right? So it's not enough time to build nuclear power. We have to focus on other solutions. That's the only way we will be able to confront climate change if we don't have any chance at all of dealing with it. So let me finish by giving you a few take-home messages. I think it's all but impossible to make an economical case for nuclear power today. new technologies, whether it is fast breeder reactors or advanced heavy water reactors or small modular reactors, are unlikely to change this picture. I didn't have time to talk about why that's the case, but I certainly explained to you why these are not going to have which are also going to face the same kind of risks as the older kinds of nuclear power plants, and there's severe problems that are inherent to the technology. We cannot escape that. So with that, I'll end. I'm happy to take any questions that you might have. Thank you.
Thank you, Professor Ramana, for a wonderful talk. And it is very interesting that two of the speakers, one had spoken about the construction and the working of a nuclear reactor, and the other had spoken the threat by constructing a nuclear reactor. And we will leave it up to the audience to decide. You have spoken about the global picture of nuclear reactors, and you have focused initially wonderfully. You have highlighted that after 70 years of starting the dream of nuclear reactor, we are only contributing around 2%, which is really very less, and something which is a big question to ask to the Atomic Energy Commission. And the other point also, like always, the Department of Atomic Energy, they have given a timeline, and always the timeline has been extended sometime because of, various reasons. Okay, I will not go to the reasons, of course. There are cases where there is public opposition, and there are risks related to radioactivity and the lifetime of radioactive materials, and the way the spent fuel has been managed. So one important point, I think everybody, the Department of Atomic Energy also should take care of this, that we have not learned the lesson from the past mistakes from all over the country. I think that is something which is a very serious point to be taken. Dr. Ramana, there are many questions already people have asked in the chat box. So if you do not mind, I will request some of them to put the questions again, and I would request you to answer those. First of all, I request Sri R.L. Patnaik, I request him to unmute and ask a question. He is an alumni of Rayagada Autonomous College, who is a part of Department of Atomic Energy. So I request Sri R.L. Patnaik to have his question.
Hello, is it audible?
Yeah, it's audible. Yes.
Sir, my question is that in one of your slide, you have shown that low-level liquid waste in nuclear power program in India is dumped to Arabian Sea and Bay of Bengal. Actually, it is not like that. Whatever the liquid low-level liquid waste or medium-level liquid waste that is generated, that has a good management plan before disposing to, and there are norms to discharge the different parameters to the event, or the main policy on which low-level liquid waste is discharged is diluted and disposed before went in a treatment plant. This is one of my attention. Again, a lot of public propaganda is active in Indian nuclear power. So many agencies are working behind through different sub-agencies to curb the power program and to stop the progress of program in India. A lot of efforts is going on from Government of India to address those situations, and nuclear power program is very transparent in India, and very good regulator is there. It is as per the IAEA norms, and all radiation protection is followed by ICRP, International Commission on Radiation Protection. Thank you, sir.
Thank you. So I am not denying that there are norms to the discharge, but I think what you're also telling me is that it does get discharged. When it is discharged, there is some radioactive levels there, and those radioactive materials have been detected. I didn't show it here, but there's sort of studies that show that you can detect it in near Tarapur, for example, right? If you collect fish from there, you can see traces of radioactive material. So that release is happening, right? It is true that Atomic Energy Regulatory Board has a set of norms, but that doesn't mean there is no radiation that is being released. That's all I'm trying to point out, right? It's whether that should be allowed or not. I think it's a different debate, right? I think that we know quite well that all levels of radiation do cause some risk of increased risk of cancer, right? And there is no threshold below which radiation is safe, right? This is sort of globally accepted. If you look at, for example, the BEAR report, the biological effects of ionizing radiation that came out of the National Academy of Sciences in the United States, they say it very clearly, right? So that there is some risk. We can decide whether it is okay or not, but that decision ought to be taken democratically. Secondly, I think your point about, there is a lot of propaganda and so on. I mean, I think there is propaganda on both sides, right? The Department of Atomic Energy continuously provides propaganda. I showed you examples of the Atomic Energy Commission chairman saying our reactors are 100% safe. Well, there actually have been accidents. So it's obviously not 100% safe, right? So both sides are engaging in this. There are also, I agree, there are many people who are making untenable statements on the other side as well, right? Trying to say that, oh, these are all sort of foreign funded and so on, I think is a very dangerous tactic, right? Because that's basically trying to refute any kind of legitimate criticism as well, right? So trying to say, if you say this, then you must be a spy, you must be a foreign agent. I think that's not the way to conduct a democratic debate.
Okay, thank
Thank
you.
you, sir. This discussion will continue. So many other persons are there, and always the motto should be for safe operation and safe. Thank you.
Yeah, I think if we leave Dr. Ramana and Dr. R.L. Patnaik to have a discussion, I think it will continue for days, because one who speaks against the construction of the reactants, the other one gets a bread and butter from the reactor. I think I have the liberty of saying that. But anyway, we have another question from Rajendra Sethi, who has asked an interesting question. Should nuclear power plant be sited underground to help contain the radioactive release? This is a question from Mr. Rajendra Sethi, and one person from Department of Atomic Energy who has worked, Girish Padhi, he has already answered to this, that underground power plant, power plants, it will increase the cost of construction, the length of lead time, and there is no guarantee of safety. That is what he has to say. Do you have something to say, Mr. Ramana, on this?
I totally agree with that. I mean, as I mentioned, the major challenge for nuclear energy has been costs. So anything that you do to increase the cost is only going to make it less relevant. And there is no guarantee even then. Exactly. So there are some risks which are also present in underground plants, which may not be so present elsewhere. For example, the risk of flooding, which is not going to be so easy in the case of a plant that is above ground.
Okay, there is a question from Dr. Manasi Mohanty. The developed world always blames the developing countries for filthy air quality and air pollution, while boycotting and violating many climate change accords. The filthy air quality debate is going on in the last few days. How does nuclear energy reduce pollution? Should the capitalist world subsidize nuclear power plants to counter global warming and climate change? This is a question posed by Dr. Manasi Mohanty.
That's a very interesting question. Definitely, one of the attractions of nuclear power is that it does not produce smoke. Right? This is why, not only is it sort of pollution, but also carbon dioxide. I completely agree with that. Right? That's why I even asked the question, should we use it as a solution for climate change? Should the developed world, the capitalist world, subsidize nuclear power? There are sort of two answers to it. The first is that, as you have rightly characterized them, capitalist countries, they're not in the business of subsidizing things to the extent that they want, right? If they'd been interested in doing that kind of stuff, a long time ago, we would have been out of this problem, right? So you're asking something about a set of countries that are not going to do it. But the second question, I think, is more important, which is that to the extent that there is such a subsidy available, should it be going to nuclear power, or should there be other alternatives? And what I would argue is that when there are so many better alternatives, if you're going to invest cost in trying to clean up India's power sector, you would invest it in solar, in wind, in trying to deal with the intermittency that comes from them, in biomass, all kinds of options that are there, rather than on subsidizing an already very expensive source of power.
Okay, thank you. Now there is a question from Dr. Girish Kumar Padhi. He says, looks like the nuclear energy is bringing all sort of problems. Is it worth spending the money in some alternative, something like solar?
Yes.
I think you have answered that. In your talk itself, you have answered that. So would you like to add any point on that?
No, I think that, that's what is happening around the world. If you look at the kind of investments that are going from the private markets into solar energy and wind energy today, solar in particular, that's much higher. In fact, the International Energy Agency came out with a report just recently saying essentially that solar energy is going to be king, that it's going to be the dominant technology going in the future. So I think that's something which, it's not just me, a lot of people are saying exactly the same thing.
Is there any question from Dr. Jagadishwar Rao, the speaker, the first speaker? Do you have something to say on counter to what Professor Ramana says, sir?
It is nothing that actually we have given an overview of both sides of the coin.
Yeah.
I have not taken much positive because I thought to explain the nuclear what it is for a learning stage. Otherwise, we can also have a lot of points, but each technology has some other negatives. That which is the better, and we never say that we should stop funding for the alternative electricity generation projects. It is one of the alternative. Nuclear should go, and whatever commission says, it is correct. We never have a accident so far. Whatever the accidents, it is like our kitchen accidents where we can have while cutting, we can cut our hand. It is not that a big accident happened in the kitchen, so tomorrow we should not use the knife. Correct. It is to be handled in a proper way. The small accident happened, and you agree that India is indigenously developing all these, and in the PHW's construction, we are attained some level of constructing it. And fast breeder, I agree surely, and it is a new technology, and India is learning, and allow India to learn and show their power in the coming days. If you stop now itself in the initial stage, no one can learn and show the power of it. So it is like a brain change, and it is going ahead. And I hope the nuclear will show the promise, and surely it will help to produce power with less cost, with less emissions.
So I think the answer I would have is yes. India has every right to try to do anything it wants, but imagine you're driving on a road, and there is a road that's going to the left, and you see there's a bunch of cars that are coming back from there, and they tell you, look, that's a dead end, don't go that way, right? And you say, no, I have the freedom to go that way, I am going to go that way. You can go, right? You're just going to waste your time going down that dead end, because you know that this breeder reactor technology is not going to actually produce cheap power. We know that for sure. We know that it is operationally problematic because of fundamental technical features, right? Liquid sodium reacts in certain ways, and that's a fact of chemistry. It's not going to go away because it's India or it's China or it is Russia, right? All of those things are going to be universal, and those problems are going to remain, right? And so there is that's what we mean by learning, that you look at other people's experience and you say, what is the best thing that we can do, right? So, I mean, of course, I realize that you're not going to agree with me because we happen to sit in sort of different places, right? But this is what I would say, that I don't think that it is going to become any cheaper, while other things are clearly becoming cheaper. So it's another thing which I want to say is that, yes, we need multiple sources of energy, and we are trying, there are many things that are being done. That said, when somebody is hungry, you need to give them food that is sort of nutritive and affordable, right? If you say, well, I'm going to feed them only sort of kheer or something like that, which is expensive and not necessarily available in large quantities, then obviously that person is going to remain hungry for a long time, right? So that I think is the problem with sort of trying to say nuclear power is going to solve the electricity problem. I don't think it is going to be a good solution. Or for climate change for that matter.
Thank you, Professor. There is a question from Dr. T.R. Devidas, who is from Israel actually. Now, while the argument for solar cells seems convincing, production of solar cells invites toxic chemicals such as arsenic, selenium, etc. And the toxic end products are dumped back into the ground. These two and intergenerational damage. Hydropower displaces whole ecosystem, which again is an intergenerational damage and cost-wise. So, do you have something to say on this? He says that there are issues on solar cells also, like the arsenic and selenium. Of course, they are toxic chemicals. They are dumped into the ground.
So so there are two things. Just like in the case of nuclear power, we are not dealing with the question of just throwing the waste anywhere, right? We are talking about repositories, trying to manage them and so on. And I'm saying there is a residual risk just after that. If you try to manage the waste from a solar production as well, you can do so in more better ways and in worse ways, right? And so we have to take the assumption that they are being dealt with in the best possible way. But there's a fundamental difference between those kinds of waste and radioactive waste. The waste that are coming out of solar panel production and so on are not radioactive. So you can try to deal with them chemically and set them aside, because these are sort of things which are found in nature. In a nuclear plant, you're producing materials which are just not found in nature, right? There is no technetium-99 in nature. There is no cesium, a whole bunch of cesium isotopes which are found in nature, right? All the radioactive isotopes. So we are talking about a very different class of waste, right? Now, it is not, I'm not saying that all, hydropower has its impacts, solar power has its impacts. That is, of course, accepted. But not all impacts are equal, right? And lastly, you also have to ask the question, okay, so, how do we decide how we do this, right? This decision should be something which is done democratically, where many people ought to be involved in the discussion, right? And this discussion should be based on clear and balanced information, right? So there is a risk involved with nuclear power plants. There is a risk of radioactive waste contamination, and those things have to be put on the table. And if you put on the table, and if you look at the costs and everything, you will probably find that in most democratic debates, people would say, okay, we are willing to live with the risk of solar power, maybe not a large dam, definitely not a nuclear power and power plant and so on. So there are these different advantages and disadvantages. When you weigh, you can sort of predict what the answer is going to be.
Okay, thank you. Thank you. Now, there are a couple of people, they have raised a hand for this. Can I request Professor Pooja Patnaik to have her question? Okay. Is there any other person who want to have a question? It's because all of them, those who asked the question to Professor Ramana, interestingly, Dr. T.R. Devidas, Dr. Girish Padhi, and Dr. Jagadishwar Rao, and Dr. R.L. Patnaik, all of them, they belong to Department of Atomic Energy. And in fact, I was also a part of that. So is there any other person who is not from Department of Atomic Energy has to ask some question? Okay, in that case, I think if there is no more questions, I thank
I see a hand up from Ramesh Chandra Huika, is that right? I see a hand up.
Oh, is it Ramesh, sir? Do you have a question? Yes, Ramesh, sir.
Okay, I guess not.
Hello.
Yes,
Sir, in our country, how your employment will be mostly generated, sir, in nuclear sector? Employment job
Employment. Yeah. So that's a great question. I mean, so I think employment is not a unitary category, right? So different kinds of technologies are going to employ different kinds of people, right? So if you happen to be a radiation biologist or a nuclear chemist, then the only kind of industry that's going to employ you is nuclear industry, right? Whereas if you happen to be specializing in let's say wind technology, then it's a wind technology is going to employ you. So that's one thing about sort of the kind of employment which is highly skilled, which is kind of more of interest to people like you. And so there are going to be opportunities and all of this, but in terms of numbers overall, most studies around the world show that nuclear power tends to employ the least number of people per megawatt of installed capacity, right? So there was a study from Berkeley, University of California, Berkeley, many years ago, which showed that nuclear power employs about a sixth of the number of people that would be employed by the same capacity of solar power. Now, if you couple that with the fact that nuclear power plants are much more expensive, so you have to spend less on producing solar power, then per unit of investment, there is much more employment to be found in other technologies. The last thing I want to say is that even if you stop building nuclear plants, unfortunately, because of the long-lived nature of nuclear waste and reactors and so on, there's actually going to be employment for many decades in just cleaning up the environmental harms produced in these nuclear power plants. So it's not as though there's going to be there's going to be a lack of employment for large number of people.
Thank you. Is there any other question to be asked by someone? Anyone else? If not, let us thank Dr. Jagadishwar Rao and Professor M.V. Ramana for two wonderful talks. Actually, most of the times we do seminar and people speak on a similar topic, but this is one of the wonderful occasions for all of us, that someone who speaks completely on the reactors and construction of reactors and all the science behind that, and the other one speaks about the safety of environment, I mean safety of the world. So it is very interesting. And my appeal to all the participants is like, rather than some politicians comes and say we want reactor, or some politicians comes and say we don't want reactor, I wish you should take your opinion from people like Dr. Jagadishwar Rao and people like Professor Ramana, rather than taking it randomly from some politician. That will be a neutral point for me to say, you can have your own opinion on that, whether to have a reactor or not, but take it from the wise people. So with this, I thank both the speakers. It's an honor, it's a pleasure to have people of your reputation in a college like Rayagada Autonomous College, which is located at a remote location of Odisha. We say this often is because we want to conduct such programs, but because of many issues, we fail to do that. And I was in contact with Dr. Ramana from last 1 year, and we scheduled this program to be conducted in February, but somehow it got shifted, and then examinations came, and then the COVID pandemic situation. And still, after 1 year, I think it is very pleasant, and it got materialized. And it is really the staff members of Rayagada Autonomous College are thankful towards Professor Ramana for giving his time, though he has come on a vacation to India. So thank you very much, sir. So I thank the principal of Rayagada Autonomous College on this occasion. She has been very kind enough to say yes for everything, almost any kind of proposal you put to her. She says yes whenever it is constructive. So thank you, madam, for giving all the support. I thank Dr. Arun Kumar Misra sir, the head of Department of Chemistry, Dr. Arun Khadanga sir, the head of Department of Physics, and all the staff members of Department of Physics and Chemistry and Rayagada Autonomous College, who have supported to conduct this half-day webinar, the international webinar. And also I thank all the participants, actually around 350 number of participants they have registered, and more than 250 they have attended this webinar, and most of them are till now active, which is a very good number. And people from various countries across the globe have participated. Actually, to be honest, we have not accepted this kind of response from people. We thought like, okay, there will be some UG and PG students, but I think this has been a wonderful response from people. So I thank everyone, but especially I thank Dr. Manasi Mahanti, because she is the person who has given that ignition that, okay, let us invite Dr. Ramana, because she knows her personally. So I thank Manasi Madam for igniting the idea of having this webinar in our college. At the same time, I thank all the organizing committee. I thank Sri Sumant Sahu sir from Department of Physics, who has done wonderful job for all these technical supports. And I thank all the staff members and everyone. Thank you very much. We will send your certificates. It will take some time. Give us some 10 days of time. Whoever has participated, we will give you the participation certificates. If you have any queries, please send a mail to me in the given email ID. And with this, I thank you everyone. Namaskar.
Thank you. Thank you very much. I really appreciate this opportunity. There's, almost no way I could have actually met with all of you, at least sort of virtually, apart without this invitation. And this is really a great opportunity for me. Thank you so much.
Thank you. Thank you for a nice organization.
Thank you. Thank you.
Now the meeting is over.
Thank you.
Now the meeting is over, and
Thanks.
the participants, they may leave the meeting. Thank you.